Hello, fellow sapiens. Sit back, relax, and prepare to meet your ancestors. Whether you're trying to fall asleep driving through the night or working with quiet company, this space is for that. Imagine this. The air still carries the ash of an extinction. The world is quiet, not with peace, but with absence. Forests that once trembled under the footsteps of giants now rustle only with wind and falling dust. The age of dinosaurs has ended, not with a whimper, but with fire from the sky. 66 million years ago, a 10-kilometre-wide asteroid struck what is now the Yucatan Peninsula, punching a hole through the atmosphere and rewriting the script of life. In the minutes that followed, shock waves rolled across continents, forests burned, and tsunamis climbed mountain valleys. In the months that followed, the sunlight dimmed, photosynthesis faltered, global temperatures plunged, a cold darkness descended for years. This was the end of the great reptilian empires and the beginning of something smaller, warmer, and infinitely more curious. When the skies cleared, the survivors emerged, not the most powerful but the most adaptable. The mammals, who had lived in the shadows for 100 million years, finally stepped into the open. They were small, nocturnal, and unremarkable to look at. Creatures with whiskers, sharp noses, and high metabolisms designed for endurance in the cold nights that followed. For tens of thousands of generations they had hidden from the giants that ruled above them. Now, with those predators gone, the forest became their new frontier. The early Paleocene world was unlike the one that died before it. With fewer plant-eating dinosaurs to mow down vegetation, forests thickened. Tropical and subtropical plants spread north and south, forming canopies over what had been open plains. In these tangled new ecosystems, insects multiplied, fruits evolved, and flowers began to experiment with new colours and scents. It was a laboratory of life starting over from near zero, and from this chaos, the ancestors of primates, our ancestors, began to take form. The earliest known of these creatures is called Purgatorius. Its fossils, found in what is now Montana, are tiny. Jaw fragments, teeth, ankle bones no bigger than a fingernail. Yet from these fragments, we see the outline of something new. Purgatorius lived in the trees that sprouted in the aftermath of the impact. Its flexible ankles suggest it could grip branches. Its teeth, broad and low-crowned, hint at a varied diet, fruit, insects, maybe even leaves. It wasn't a primate as we understand the term today, but it carried the potential in its limbs and jaws. It is the oldest known member of the primate line, appearing barely 500,000 years after the asteroid struck. To understand what made this possible, we need to picture Earth as it was then, a recovering organism. The continents were arranged differently, but Africa was already in the position that would matter later, straddling the equator, warm and fertile. The poles were still capped with temperate forests. Atmospheric carbon levels were high. With the death of so many species, niches opened everywhere. Mammals diversified rapidly. Some became burrowers, others gliders, and still others climbers. Evolution began 1,000 simultaneous experiments. The small creatures that clung to branches at night, with their quick hands and sharp eyes, were one of those experiments. Paleontologists call this time the Paleocene recovery, a long biological improvisation. For nearly 10 million years, mammals exploded in number and diversity. In fossil beds from Wyoming to Morocco, we find their teeth scattered like punctuation in the story of life. Most of these early mammals wouldn't last. Some lines dead-ended in a few million years. But one branch, the early arboreal mammals, found a lasting advantage, a three-dimensional world of safety and food above the ground. the forest canopy became a new continent in itself, unreachable by most predators and rich with fruit and insects. Evolution rewarded those who could grasp, balance, and see in depth. At first, these adaptations were small, a longer toe here, a rotating ankle there. The changes were subtle enough that a casual observer wouldn't have noticed a difference from the shrew-like mammals that came before. But over evolutionary time, such details become destiny. The eyes of these tree dwellers began to shift forward, overlapping slightly to improve their range. Their claws flattened into nails for better control. Their brains enlarged to manage the complex geometry of branches and shadows. None of this happened overnight. It took tens of millions of years. But it began here, in the green twilight after catastrophe. As continents drifted, the world itself changed shape. By 55 million years ago, the Atlantic Ocean was widening. India was racing toward Asia. Volcanic activity was releasing greenhouse gases, triggering the Paleocene-Eocene thermal maximum. A brief, intense warming that turned Earth into a near-tropical planet. Forests grew as far north as what is now Alaska. This warming may have pushed the early primates further into the trees, reinforcing their arboreal lifestyle and spreading them across connected forest belts from North America to Africa. For them, it was a golden age of green corridors. When paleontologists study this era, they often find themselves reading the subtlest signs, tiny bones, chemical isotopes, the angle of an ankle joint. Each piece tells part of a larger story, that life, given time, recovers not by repeating what it lost, but by reinventing itself. After the dinosaurs, Earth didn't rebuild the old order. It invented mammals that could think and plan, creatures whose future would depend less on strength than on imagination. It's humbling to remember that our story begins not with conquest, but with survival through luck. If the asteroid had struck a few minutes earlier or later, if the winds had shifted differently, perhaps the mammals we descend from would not have made it. Perhaps a different branch of life would have filled the empty world. Evolution is never inevitable, it's just persistent. As the Paleocene dawn unfolded, the forest buzzed again with sound. Insects reclaimed the air. Small mammals scurried across trunks. The planet was healing, and with that healing came experimentation. Every twig, every leaf, every shift in climate provided a new challenge, and life met it with invention. Somewhere in that vast experiment, one tiny mammal learned that balance could mean survival. The ability to cling to a branch became the first gesture in a long chain of adaptations that would one day produce a hand capable of shaping stone, building fires, and writing stories. When we picture those early mammals, soft-furred, bright-eyed, darting through primeval foliage, it's tempting to see ourselves already in them. But we must be careful. They were not us. They were the beginning of a long evolutionary poem still being written. What links us to them is not form, but endurance. Their descendants would weather ice ages, mountain births, and continental separations. Each catastrophe would prune and refine them until, much later, one branch learned to look back and ask questions about beginnings. If you were to stand quietly in that Paleocene forest, you would hear the first faint stirrings of the lineage that would become human. Leaves whispering under tiny feet. Eyes adjusting to filtered light. A pulse of curiosity moving through a creature that has no name, no thought, only instinct. And yet, somewhere inside, the architecture of awareness is beginning to take shape. The same light that glows through your own eyes tonight once touched theirs. It was weaker then, filtered through ash and humidity, but it illuminated the same essential impulse, to move toward warmth, toward possibility. The story of humanity begins not with dominance but with vacancy. The dinosaurs left an opening, and life filled it with patience. From that patience came invention, and from invention, consciousness. In the fossil record, it looks mechanical, bones and layers of sediment, but behind every fossilized fragment is a lineage of survivors who adapted without knowing why. They didn't need to know. Nature experimented for them. If the end of the dinosaurs was a closing act, the first primate ancestors were the overture to something astonishing. Life didn't just resume, it diversified into forms that would one day question the very process that made them. We are the product of that quiet restart, the echo of a world that rebuilt itself from ash and silence. The next time you look up at the night sky, remember, we owe our existence to a collision that almost erased life itself. From destruction came curiosity. From a silence came eyes that would one day watch the stars and wonder how it all began. And that, as far as we can tell from the fragments of bone and dust we've uncovered, is where our story opens, on a planet learning how to live again. Welcome to Sleepless Homo, a corner of calm for tired thinkers. Here, we tell stories softly, humble science, deep time, and the quiet wonder of what we actually know so far. No noise, no drama. Just archaeology, evolution, and the strange beauty of being human. If you enjoy this kind of slow storytelling, calm, factual, and human, you can like or subscribe to help other sleepless minds find it. Now, imagine this. The world has become a garden again. 55 million years ago, Earth breathes warm air thick with humidity and scent. Forests stretch nearly from pole to pole. There are no icy caps yet, only endless green. The land that will one day be Europe is a tangle of vines and giant leaves. What will become Wyoming is a tropical wetland steaming under monsoon skies. Among the trees, branches twist in layers so dense that sunlight filters through like liquid gold. It is a planet run by plants, pollinators, and the small mammals that learn to trust the trees. This is the stage on which the true primates appear, the first to truly see, to grasp, to think ahead. Their ancestors, small creatures like Purgatorius, had already taken the first tentative steps into the canopy. But these new species, the adapids and amomiids, were something different. They were not improvising their way through branches. They were born for them. Their wrists rotated freely, their fingers curled gently around bark instead of digging in with claws, and most remarkably their eyes turned forward, giving them depth perception. In this new forest world where danger and food existed in 3 dimensions, seeing distance could mean the difference between landing or falling. The air of the Eocene epoch was warm enough to make even the Arctic Circle host to lush forests. The poles had spruce and palm trees, dragonflies and frogs. It was an age of abundance, and with abundance came specialization. Insect eaters refined their hearing. Fruit eaters refined their vision. For primates, the forest canopy became both home and laboratory. The fossil record tells us these early species lived their entire lives in the trees. They slept in tangled nests of leaves, gave birth on branches, and fed on the flowers and fruit that bloomed endlessly under the Eocene sun. The adapids, often compared to modern lemurs, were diurnal, active in the daytime. Their faces stretched forward with long snouts, and their eyes were smaller, suited for bright light. The amomiids, their nocturnal cousins, had enormous forward-facing eyes, each socket nearly half the size of their skull. Some species of omomiid, like Talardina, could have seen in the dim glow of dawn with extraordinary clarity. Between these two groups lies the root of what would become all later primate diversity. One lineage leaned toward daytime life and fruit-filled diets, the other toward darkness and insect hunting. Both lines carried the tools that evolution would later refine into human perception. When you think about what it means to see in depth, you're really thinking about time. Binocular vision lets an animal judge the future. How far away a branch is, how fast prey is moving, when to jump or reach. It turns movement into prediction. Evolution built this ability slowly, as tree dwellers that misjudged distance simply didn't live long enough to reproduce. Over millions of years, those with slightly more overlap in their visual fields passed on that trait. In the fossilized skulls of adapids, the eye sockets are perfectly forward, like two lenses focused on tomorrow. Fossils from Messel in Germany, a lake bed that captured life in exquisite detail, show us what they looked like in death. There, beneath layers of oil shale, scientists have found the remains of Darwinius macile, a young female with fur, stomach contents, and even fingernails preserved. She was about 9 months old when she fell into a volcanic lake 50 million years ago. Her hands have 5 fingers with nails instead of claws, and her thumbs oppose slightly. She was grasping when she died. In those tiny nails lies a revolution. Claws are good for clinging, nails are better for touching. They allow precise feedback, a constant conversation between finger and branch. Every primate since has carried that tactile language forward. If we could follow Darwinius through her forest, we would see her move with the deliberate grace of an animal that trusts its balance completely. She would climb toward patches of fruit, bright red or purple spheres that stood out against green leaves, and she would reach, not leap blindly. Her brain, about the size of a walnut, processed the world as a map of possibilities. The fingers that grasped fruit would one day grasp tools. The eyes that judged distance would one day measure stars. What drove this sudden flowering of primate forms? The answer, as always, seems to lie in food and climate. Around 56 million years ago, Earth underwent a dramatic heat spike known as the Paleocene-Eocene thermal maximum. Carbon levels soared, average global temperatures rose by several degrees, and tropical forests spread even further. In this endless summer, flowering plants, angiosperms, exploded in diversity. Fruits became more colourful, fragrant, and nutrient-rich, competing for the attention of animal dispersers. For primates, this was the perfect opportunity. Colour vision evolved to distinguish ripe from unripe, sweet from bitter. Some scientists argue that red-green colour sensitivity, present in many primates today, originated exactly in this moment. A response to a forest that suddenly became too rich to navigate without selectivity. This shift had another consequence. A fruit-based diet meant mobility. Fruit doesn't ripen evenly across a forest. Finding it required memory and spatial awareness, traits that nudged the primate brain toward complexity. Where earlier mammals relied on smell and instinct, primates began to rely on visual mapping and planning. Each tree became a coordinate in a mental geography. To survive, you needed to remember not only where food was, but when it would be there again. The forest demanded memory, and memory in turn demanded a bigger brain. By 48 million years ago, this experiment had succeeded. Primates had spread across Africa, Asia, and Europe, diversifying into dozens of species. Some evolved elongated limbs for leaping, others shortened them for cautious climbing. Their teeth revealed diets ranging from insects to nectar to hard seeds. This period marks the beginning of what scientists call the primate adaptive radiation, an evolutionary bloom that would later set the stage for monkeys, apes, and eventually us. And yet, their world was not static. The Eocene forests were dynamic, prone to monsoons, storms, and constant competition. Trees fell. New growth erupted. Predators, including early carnivores and snakes, prowled the canopy. Survival required not only agility but awareness. In this living maze, natural selection favoured individuals that could pause, judge, and act deliberately. The leap from instinct to intention may have begun as a physical act, calculating distance between branches, but its echoes still live in every decision we make. If you close your eyes for a moment and imagine standing on a branch 50 feet above an ancient swamp, you might feel the pulse of that early cognition. The weight shifting in your ankles, the subtle adjustment of balance before you move, the quiet confidence that the next branch is close enough. That trust in space, the ability to measure risk, was the first expression of foresight. Our lineage was learning to think through motion. Each grasp reinforced neural circuits that connected touch, sight, and timing. Over evolutionary time, those circuits grew denser, more refined. Touch became a teacher, not just a sense. The fingertips of early primates had more nerve endings than those of any other mammal of their size. Through them, the forest communicated information. Bark texture, fruit firmness, the tremor of insects underneath leaves. Evolution was, in a way, sculpting curiosity into skin. These early primates were also social. Fossil sites often yield multiple individuals, suggesting group living. In trees, safety lies in numbers. They likely groomed one another, removing insects and maintaining bonds through touch. This behaviour, seen in all modern primates, may have its roots here. Touch became not only a way to navigate the physical world, but also the social one. A gentle stroke meant reassurance. A shared fruit meant alliance. Beneath a canopy, the first forms of empathy were being rehearsed. Scientists continued to debate whether adapids and amomiids were direct ancestors of later primates, or simply close relatives. The fossil record is incomplete, and small bones rarely survive intact. But whether they led directly to us or merely paralleled our path, they represent a crucial step. Mammals whose world expanded vertically and mentally at the same time. As the Eocene progressed, climates began to fluctuate again. Volcanic activity, shifting ocean currents, and slow tectonic drift subtly altered rainfall patterns. Some forests fragmented into patches, isolating populations and pushing evolution in different directions. Those isolated groups developed new diets, new behaviours, and slightly different anatomies. Each small divergence would later echo through the branches of the primate family tree. If you could lift the canopy and see Earth from above during this time, it would look like a living circuit board. Forests connected by narrow corridors, each buzzing with life. And hidden within that circuit were the first sparks of cognition that would, much later, ignite self-awareness. The adapids and amomiids did not know they were shaping history. They were simply surviving, eating, leaping, sleeping. But in doing so, they were refining the very abilities that would define intelligence itself. The gift of vision, the precision of grip, the patience to wait for ripening fruit. These were not just survival strategies. They were rehearsals for the human mind. Each adaptation whispered a future possibility. When Darwinius reached for a fig, she was not thinking of the distant descendants who would hold tools or write equations, yet the motion was the same. It was an act of faith in the material world. Trust the branch. Trust the distance. Trust the reach. In the end, the rise of true primates was not sudden brilliance, but a slow symphony of adjustments. Touch, sight, coordination, curiosity played out over millions of years. Each generation fine-tuned a different note until eventually the melody of intelligence began to take shape. We may never know exactly which species marks the first creature we would call a primate. The fossil record gives us hints but not closure. What we do know is that somewhere in those ancient forests, a lineage learned to see differently, not just with eyes, but with attention. The world became three-dimensional, not only in space but in meaning. If you ever wonder when our ancestors first looked at their surroundings and felt a spark of comprehension, you might imagine a small animal perched quietly on a branch at dusk, eyes catching the last light of the Eocene sun. It blinks, adjusts its grip, and leaps perfectly precisely to the next branch. And in that leap the story of perception begins. Tell me where you're listening from, before sleep, on headphones, or somewhere in between, and if you drift off, timestamps are waiting when you wake, and as always, stay curious, stay calm. Imagine this. An ocean the size of a continent slowly vanishes, its warm waters folding into the earth. Where once there was sea, islands rise like stepping stones, bridging two worlds that had never touched before. Asia drifts toward Africa, drawn by forces buried deep beneath our feet. What began as molten movement in the planet's mantle, it will soon decide the fate of our lineage. The continents are not still. They breathe in geological time. They close distances, share climates, and exchange life. And in one of those exchanges, something small, barely the weight of a mouse, will set the stage for everything that comes next. Around 40 million years ago, Earth's surface was alive with motion. The land masses were slowly arranging themselves into something we would recognize today. The Indian subcontinent was colliding with Asia, raising the first folds of the Himalayas. To the west, Africa and Arabia were moving northward, closing the ancient Tethys Seaway, a shallow ocean that had once separated them from Eurasia. The air was warm, the seas rich with plankton, and the forests still covered much of the tropical belts. Yet this slow tectonic ballet would change more than geography. It would open doors for migration and evolution, linking populations that had been isolated for tens of millions of years. In the fossil record, this transition is mirrored by a subtle but profound evolutionary leap, the rise of the first higher primates. These creatures, known to scientists as anthropoids, are the ancestors of monkeys, apes, and humans. Their origins were long debated. For decades, fossils found in Africa seem to suggest the continent as their birthplace. But the discovery of tiny bones in Asia began to rewrite that story. In the red clays of central China and Myanmar, paleontologists uncovered a genus called 𝐓𝐈𝐌𝐄𝐒𝐒, the dawn monkey. Its fossils are minute, jaws, teeth, fragments of ankles and wrists. Yet in those fragments, scientists see traits familiar to later monkeys and apes. The ankle bone, in particular, reveals how it moved, an agile leaper, capable of grasping branches with precision. Its teeth show a diet of insects and fruit, suggesting a life lived in the upper canopy, quick and deliberate. Radiometric dating places 𝐓𝐈𝐌𝐄𝐒𝐒 at roughly 45 to 40 million years ago, making it one of the earliest known anthropoids. The presence of these fossils in Asia sparked a quiet revolution in primate paleontology. If 𝐓𝐈𝐌𝐄𝐒𝐒 lived here first, then Asia may have been the cradle of the higher primates. Africa, long assumed to be the beginning, might instead have been the stage they later migrated to. But how could these tree dwellers cross the vast Tethys Seaway that once lay between continents? To answer that, we have to descend beneath the surface, into the planet's slow machinery. Beneath the crust, the mantle moves in currents of molten rock, rising and sinking like a global lava lamp. These movements push continents apart or pull them together. Around 40 million years ago, one such upwelling known as the Afar Plume swelled under northeastern Africa and Arabia. The rising heat ballooned the crust, creating volcanic plateaus and lifting the sea floor. Over time, this uplift, combined with the northward drift of the African and Arabian plates, began to close the Tethys Seaway. Where water once flowed between Africa and Eurasia, new islands began to emerge, volcanic arcs and coral platforms forming temporary bridges. It would take millions of years, but these changes transformed isolation into opportunity. Forests crept over the new land masses. Animal lineages that had evolved separately now found new routes to explore. Rodents, ungulates, and early primates began to move between continents. The geological record preserves this moment as a pulse of migration, fossils of Asian mammals appearing in African strata and vice versa. The Earth, in its restlessness, was cross-pollinating life. It's humbling to imagine how random this connection must have seemed. A few degrees of tectonic tilt, a handful of new islands, and suddenly the history of primates changed forever. 𝐓𝐈𝐌𝐿 and its kin may have been among the travellers, or their descendants may have been. Whether they crossed on forested archipelagos or drifted along vegetated rafts torn from shorelines by storms, their movement into Africa set the stage for the next phase of primate evolution. The world they moved through was unstable but vibrant. Temperatures were beginning to cool after the long Eocene heat. Rainfall patterns shifted as mountains rose and monsoon systems strengthened across Asia. These shifts created patchy environments, tropical rainforests near the equator, drier woodlands to the north. Evolution thrives on contrast, and this climatic variety encouraged adaptation. In the fossil sites of Myanmar, Pakistan, and southern China, we see a flourishing of small primates experimenting with form and function. Some developed shorter snouts and forward-facing eyes, traits linked to better depth perception. Others evolved stronger jaws for chewing harder fruits and seeds. The variety suggests a lineage preparing for expansion, primates with the anatomy to handle multiple ecosystems. The collision of continents also had planetary consequences. As the Indian and Eurasian plates met, the rising Himalayas began to alter global weather. Their formation drew carbon dioxide out of the atmosphere through chemical weathering, gradually cooling the planet. These environmental feedback loops were slow but relentless. By 35 million years ago, ice sheets were beginning to form at the poles. The world that had once been drenched in tropical warmth was entering a long, uneven cooling trend. Against this backdrop, the evolutionary centre of gravity for primates shifted. Fossil evidence shows a decline in Eocene primate diversity in Europe and North America, likely driven by cooling and habitat loss. Meanwhile, tropical Africa remained a refuge, a stable, lush region buffered by its equatorial position. When land bridges finally connected the continents, Africa was the ecological jackpot, warm, forested, and full of opportunity. The migrants that reached it would not only survive, they would diversify. This connection was not a single event but a gradual weaving together of two worlds. Over millions of years, currents carried sediments, volcanic eruptions built islands, and sea levels rose and fell with climate cycles. Each pulse of tectonic motion redrew coastlines, sometimes opening paths, sometimes closing them. We can trace these transitions in the geological strata along the margins of modern Egypt, Saudi Arabia, and the Eastern Mediterranean, where marine fossils mingle with early land mammals. Each fossil is a timestamp in a planetary relay, showing how the movements of rock and water choreograph the migrations of living things. When we speak of evolution, we often think of adaptation to climate or predation, but rarely of continents themselves as players. Yet geology is evolution's longest narrative. The shape of the planet decides where forests grow, where rivers cut valleys, and where species meet. In this sense, 𝐓𝐈𝐌𝐿 was not only a biological creation but a geological one, a life form made possible by continental drift. Without that slow closing of the tethys, there might never have been a path for anthropoids to reach Africa, and without that, the story of primates could have ended very differently. Imagine the scene from above. Two vast continents inching toward one another, separated by a chain of islands shimmering under tropical storms. Across these islands, small primates with bright eyes and flexible hands move cautiously through the branches. They are unaware of the grand stage beneath them, the tectonic dance that will eventually carry their descendants across oceans and into history. Each leap from branch to branch is mirrored, far below, by the grinding movement of plates 100 kilometers deep. One is measured in milliseconds, the other in millions of years, yet both are part of the same choreography. By 30 million years ago, the Tethys Seaway was a shadow of its former self. What remained were narrow straits and enclosed basins that would one day become the Mediterranean, the Red Sea, and the Persian Gulf. The Arabian Peninsula had welded itself to Africa, and the combined landmass was now pressing against Eurasia. This new geography not only redirected ocean currents, but also set the stage for the emergence of the African Rift System, a feature that would later define much of our species' early story. But that, of course, comes later. For now, what matters is that a bridge existed. Across that bridge, early primates, perhaps descendants of Eosimius, perhaps their close relatives, moved westward into Africa. In doing so, they carried with them millions of years. If we trace this journey not through bones, but through time, it reads like a quiet dialogue between continents. Asia offered the idea, Africa would develop it, and between them lay the remnants of an ocean that had once divided worlds. The closing of that sea is one of the rare moments when the story of the earth and the story of life merge completely, when rock and biology speak the same language of movement and change. From our vantage point today, it's easy to forget that every creature owes its existence not only to genetics but to geology. We are shaped by mountains as much as by mutations. Somewhere, in the warm forest that bordered the shrinking Tethys, a small primate watched the tide retreat from the shore, unaware that the land beneath its feet was rewriting the blueprint of the future. Its world was simply changing, as worlds always do. That is how the seed travelled, from Asia's forest to Africa's green heart, carried by nothing more than time, luck, and the restless breathing of the planet itself. Imagine this. A forest so dense that sunlight struggles to reach the ground. Leaves the size of a human torso catch the rain before it ever touches soil, and vines hang like ropes between colossal trees. The air hums with the sound of insects and the distant cries of birds that will one day have no names. It is 25 million years ago, and East Africa is a green labyrinth. Somewhere in that tangle of branches, a new kind of primate is learning how to move, to think, and to balance not just its body, but its future. The question is simple but profound. When the forest thickened, who learned to live without a tail? In this world, the first true apes are beginning to appear. They're not yet human, but they are no longer quite like the monkeys that came before. Their names, written in the bones of long-extinct forests, are Proconsul and Afropithecus. Fossils of these species found in East Africa, in Kenya, Uganda, and the Great Rift region, mark the beginning of the ape experiment. Their emergence between 25 and 20 million years ago represents one of the most important transitions in primate evolution. The shift from the flexible-tailed monkeys to the tailless apes whose descendants would one day walk upright. The story begins with Proconsul, a genus that once thrived across the tropical forests of Miocene Africa. Imagine an animal about the size of a medium dog, moving carefully across branches, its long fingers wrapping around bark with precision. It had a broad torso, forward-facing eyes, and a flexible shoulder that could swing and reach with ease. But what it lacked was just as significant as what it had. Proconsul had no tail. This single absence tells us much about its changing relationship with gravity. Monkeys use their tails for balance, especially when leaping or running along narrow branches. Apes, in contrast, rely on a different geometry, centered strength and flexible hips and shoulders to control their movement. Losing the tail was a quiet evolutionary gamble. It meant gaining a new kind of body built for suspension, not sprinting. Fossils from Rusinga Island in Kenya show how this anatomy was taking shape. The pelvis of Proconsul reveals a posture suited for life in the trees, but with a spine and ribcage hinting at future possibilities. It still moved on all fours, placing its palms flat on the branches, yet its limbs were more equal in length than those of monkeys. The balance point of the body had shifted. Evolution was preparing a skeleton that would one day allow hanging, swinging, and eventually standing. In these bones we see the architecture of potential, the scaffolding from which the great apes and humans would later emerge. At the same time, another genus was exploring similar territory. Afropithecus, slightly younger than Proconsul, found in sites such as Moroto in Uganda and Kalodare in Kenya. Afropithecus had a heavier jaw, larger molars, and thick enamel, suggesting a diet that included hard fruits and nuts. It was a forest forager built to chew resilience. Its skull shows a brain slightly larger relative to its body than earlier primates, indicating the slow inflation of intelligence that would characterize apes. The expansion was not dramatic yet. It was measured in millimeters, but even small increases in brain complexity can reshape behavior. More neurons meant better memory, more flexible problem-solving, and the early seeds of social awareness. In the Miocene forests, these apes likely lived in small, fluid groups. Fossil evidence does not preserve social behaviour, but comparisons with modern primates allow cautious inference. The balance between cooperation and competition was already being tested. Grooming, mating, and foraging behaviours probably relied on subtle communication, facial expressions, vocalizations, maybe even basic emotional recognition. To live without a tail in a three-dimensional forest required trust in one's grip, in the stability of a branch, and perhaps in the presence of others nearby. Evolutionary success, as always, favoured those who could read both trees and companions. The African forests of this time were extraordinary. Rising humidity and warm global temperatures had created a botanical paradise stretching from the equator to the edges of what is now the Sahara. River systems cut through dense jungles, forming corridors that allowed species to migrate and mingle. These ecosystems were layered and intricate. Fruit-bearing trees offered seasonal abundance, while the canopy provided shelter from predators that still roamed below. Large snakes, early carnivorous mammals, and ancient birds of prey. Living here required a balance of caution and curiosity. Apes like Proconsul were built for that balance. Their eyes faced forward not only for depth perception, but for anticipation. A mental grasp of the next branch, the next meal, the next move. The fossil record shows that Proconsul's hands were already beginning to resemble ours. The fingers were long and curved, ideal for gripping, but the thumb was opposable, capable of fine control. This combination of strength and precision marks a crucial milestone in primate history. The world was no longer navigated solely by instinct or speed. It was being explored through touch and deliberation. These apes could grasp not just branches, but also possibilities, anatomical and behavioural, that earlier primates could not. If we could stand beside one, the differences might be subtle but unmistakable. The absence of a tail would change the silhouette completely, giving the creature a more compact, upright balance. The head would move smoothly with the shoulders, eyes scanning the forest with quiet intelligence. Its movements would seem thoughtful, almost cautious, unlike the quick darting energy of monkeys. This shift from speed to control mirrors a deeper evolutionary theme, a species beginning to invest in planning rather than reaction. Another remarkable trait of these early apes was their expanding lifespan. The fossilized teeth of proconsul show slower enamel growth compared to monkeys, suggesting longer developmental periods. Longer childhood means more learning, and more learning demands more social structure. In this sense, the earliest apes were not just changing physically, they were altering the rhythm of life itself. Evolution was trading immediacy for longevity, building a foundation for intelligence that thrives on experience rather than instinct. The loss of the tail may also have had social consequences. Without that expressive appendage, apes had to rely more on facial cues and vocal sounds. The modern ape's rich palette of expressions, from curiosity to warning, may trace its origins here, when faces became the main medium of communication. The shift from tail to face marks a quiet revolution in social cognition. Body language became more nuanced, emotions more visible, and interactions more complex. Each of these changes was subtle on its own but powerful in combination. Together they transformed how these creatures experienced their world. A flexible shoulder allowed them to move not just along branches but beneath them. A larger brain allowed them to remember fruiting seasons and recognize individuals. A longer childhood allowed bonds to form and knowledge to pass between generations. The evolutionary story of the apes is therefore not just about anatomy. It's about time. More time to learn, to interact, to live. For paleontologists, uncovering this story is a meticulous pursuit. The bones of proconsul were first discovered in the early 1900s, but it wasn't until the mid-20th century that their significance became clear. Each fossil, each fragment of jaw or limb, added a piece to the puzzle of how apes emerged. Modern techniques like CT scanning and 3D modelling now allow scientists to reconstruct these skeletons in virtual space, revealing muscle attachments and motion patterns invisible to the naked eye. We can now watch, in simulation, how proconsul climbed or how Afropithecus chewed. Yet despite this technological clarity, the deeper questions remain philosophical. Why did evolution favour this form? Why give up the tail? Why risk a new design in a world already teeming with success stories? The honest answer is that we don't fully know. What we can say is that nature tends to experiment when conditions are stable enough to allow mistakes. The Miocene forests were forgiving laboratories. Falling from a tree was rarely fatal if the branches were thick and soft with moss. The abundance of fruit meant that even inefficient foragers could survive. In such an environment, evolutionary innovation could flourish. The apes were nature's boldest prototypes, creatures testing a slower, more deliberate way of living. As their populations grew, so did their diversity. Fossil evidence hints at several species of early apes inhabiting East Africa at once, each exploring different ecological niches. Some had lighter builds for quick climbing, others were heavier, perhaps spending more time on sturdy branches or the forest floor. This variety demonstrates that evolution was not heading toward a goal. It was radiating, experimenting. Only later, as climates changed and forests began to thin, would one lineage find the advantage in adaptability that led to us. But in this moment, 20 million years ago, the world still belonged to the trees. If you could listen to that ancient forest, you might hear the soft rustle of leaves, the crack of fruit husks, and the low calls of apes echoing across the canopy. Among them, a mother carries her young tightly against her chest. She pauses, looks upward, and moves on, her body perfectly balanced in the shifting light. She will never know that her kind has given the planet something entirely new, a mind complex enough to wonder about its own origins. These were not our ancestors in a direct sense, but our foundation. The tree of life needed strong roots, and the apes of the Miocene were exactly that. They inherited the forest, and in doing so they began the slow transformation of touch into thought. When the forest thickened, they adapted not by running faster or growing sharper claws, but by trusting their hands, their memory, and each other. The forest shaped them, and in return they became its most reflective creation. Imagine this. The world begins to dry. The endless green that once stretched across continents starts to fracture, and the trees, those ancient laboratories of movement and thought, begin to vanish. The air cools, the rains weaken, and the forests that shaped the minds of apes start to break apart like old memories. 17 million years ago, the age of forest was ending, and the age of adaptation had begun. What does intelligence do when the trees disappear? During the Middle Miocene, the Earth entered one of its great transitions. For millions of years, global temperatures had been stable and warm, supporting vast belts of tropical forest that reached from Africa, through Europe, and deep into Asia. But deep beneath the ocean, the planet was quietly rearranging itself. The Antarctic continent, once connected to South America and Australia, had fully separated and was now encircled by a cold, ocean current. This Antarctic circumpolar current acted like a planetary refrigerator, isolating the pole and locking away heat. Over hundreds of thousands of years, global temperatures fell, glaciers began to expand, and the humid Miocene paradise began to cool and fragment. In Africa, the equatorial forest retreated, giving way to woodlands and open habitats. In Europe, where apes like Dryopithecus had thrived in lush environments, conditions changed even more dramatically. Rainforests turned into patchy mosaics of forest and grassland, then into more temperate ecosystems as the cooling continued. The animals that had evolved in a world of abundance suddenly faced scarcity. For the apes, creatures specialized in climbing, reaching, and social foraging, this environmental shift was an existential challenge. Dryopithecus was one of the most remarkable apes of its time. It lived across Europe, from Spain and France to Hungary and Germany, around 12 to 9 million years ago. In life, it would have looked somewhat like a modern chimpanzee, with long arms for climbing and a brain slightly larger than its predecessors. Its teeth tell us it was primarily a fruit eater, adapted to a world rich in soft, sugary abundance. But as the climate cooled, fruit became seasonal, forests fragmented, and the lush canopy it depended on grew thin. In fossil sites such as Rudabanya in Hungary and La Grève in France, the bones of Dryopithecus appear alongside those of forest animals that would vanish soon after. The same layers that record its life also record its disappearance. For a while, the apes tried to keep up with the changing world. They moved across the new landscapes following the shrinking forests. Fossils show evidence of apes adapting to more mixed environments, less arboreal, more flexible. But there was a limit. The physiology built for swinging and fruit picking did not suit open terrain. Where the forests vanished completely, so did the apes. Europe, once their flourishing frontier, became a graveyard of experiments in intelligence that could not outpace climate. The contrast between extinction in Eurasia and survival in Africa tells us something essential about the geography of evolution. Africa, anchored on the equator, remained a climatic refuge. Even as global cooling intensified, its rain belts persisted, shifting but never disappearing entirely. The East African Rift region, in particular, became a cradle of continuity, a patchwork of forests and valleys where humidity lingered and biodiversity endured. Here, apes survived. There, in the changing landscapes of Eurasia, they faded into the fossil record. The decline of the Miocene apes was not an abrupt catastrophe. It unfolded slowly, like a long, quiet farewell. Over millions of years, species vanished one by one. The European ape Pierolapithecus, the arboreal Ankaropithecus of Turkey, and the island specialists that once inhabited Italy, all disappeared as conditions grew drier and cooler. The same pattern repeated across Asia. Forest corridors that had once linked continents dissolved into savannas, cutting off populations and trapping them in isolated habitats. Evolution thrives on isolation, but only if the environment remains stable long enough for adaptation to take hold. For the apes of Europe, stability was gone. Still, not all was loss. The survivors in Africa and parts of Asia carried forward the lessons of the forest into a new world. Their hands, shoulders, and social minds, shaped by millions of years in the trees, proved flexible enough to navigate uncertainty. While Europe cooled, Africa held onto its warmth, and its apes continued to evolve. Fossils like 𝐓𝐀𝐌𝐏𝐒𝐒 and 𝐓𝐈𝐌𝐿𝐄𝐒𝐓𝐀𝐌𝐏𝐒, found in East Africa, show transitional features: thicker tooth enamel for harder foods, more robust limbs for mixed terrain, and subtle changes in posture. These species represent an evolutionary resilience, life learning to adapt not by specializing further, but by broadening the range of what it could endure. Scientists studying the isotopic composition of ancient soils and teeth from this period can trace the environmental shift in remarkable detail. Carbon isotopes reveal the spread of grasses that rely on different photosynthetic pathways from trees, a chemical fingerprint of open landscapes replacing forests. Oxygen isotopes in fossilized enamel record cycles of drought and rainfall, showing that the climate was not only cooler, but also more variable. This environmental volatility may have been one of the greatest selective pressures in primate history. It rewarded flexibility over perfection, innovation over repetition. The shrinking forests also reshaped behavior. In denser habitats, apes could rely on stable social groups and predictable food sources. But as patches of forest grew smaller and more dispersed, survival demanded movement. Populations fragmented. Groups had to navigate greater distances between food sources, perhaps even venturing onto the ground more frequently. Social networks would have been tested, hierarchies strained, and cooperation redefined. The complex emotional lives that characterize modern apes may have been forged under this very pressure. The need to maintain trust and communication while the world shifted beneath them. In the fossil record, 𝐓𝐈𝐿𝐄𝐒𝐓𝐀 is more than just a vanished species. It is a symbol of potential unrealized. Its brain, relative to its body size, was already approaching the proportions of later apes. The structure of its inner ear and jaw suggests fine motor control and perhaps a more nuanced vocal repertoire. It was, in many ways, an experiment in intelligence that the Earth did not keep. If the climate had remained stable, perhaps 𝐓𝐈𝐿𝐄𝐒𝐓𝐀 or its relatives might have continued evolving along a different path. But evolution has no sentiment. It moves with the weather, and the weather was turning cold. By the late Miocene, around 9 million years ago, Europe's last apes were gone. In Asia, a few isolated lineages held on longer, giving rise to the ancestors of modern orangutans. But the centre of primate innovation had shifted decisively back to Africa. There, the forests and woodlands of the Rift Valley sheltered the ancestors of future lineages, gorillas, chimpanzees, and eventually humans. Africa's stability was not absolute. It too experienced cooling and drying. But compared to Europe's collapse, it remained a sanctuary, a place where complexity could persist. The story of this time is not only about extinction, but also about what extinction teaches. When the world changes too fast, specialization becomes a trap. The same traits that once guaranteed survival, perfect adaptation to the canopy, reliance on fruit and narrow diets, became vulnerabilities. Intelligence, as it turns out, must also evolve. The apes that survived were not the smartest in any modern sense. They were simply the most adaptable, the ones that could hold on to their inherited skills while improvising new ones. Evolution rewards not the cleverest, but the most flexible mind. What makes this period so fascinating is that it compresses geological and biological change into a single narrative. Tectonic shifts altered ocean circulation, which altered temperature, which altered vegetation, which altered life. The apes were participants in a story written by wind and water. Their decline was not failure, it was adjustment written at the wrong speed. For us, tracing their fossils is a reminder that even intelligence cannot stand still when the Earth itself is in motion. In Hungary's Rudabanya quarry, paleontologists still uncover fragments of Dryopithecus. A jaw here, a wrist bone there. Each fossil is a record of adaptation caught mid-thought, of a species that nearly bridged two worlds, the lush canopy and the uncertain open ground. Holding those bones, one feels both the intimacy of kinship and the distance of extinction. We are the descendants of survivors, but the line between survival and disappearance is measured not in brilliance, but in luck. When the Miocene forests broke apart, the apes faced the oldest test of intelligence, to change or to vanish. Some failed, trapped in a body and a diet that no longer matched the world around them. Others, somewhere deep in Africa's surviving green corridors, endured by changing their habits, exploring the ground, and trusting the instincts written in their hands and eyes. The forest had made them intelligent. Its loss forced them to become adaptable. In that quiet, slow catastrophe, evolution rehearsed a lesson it would repeat many times. Every advantage carries the seed of its own undoing, and every loss creates space for something new to begin. An ape stands upright for the first time. The forest around it is thinning, the air drier than before, and the ground no longer feels like a passing surface, but a new world underfoot. In this strange in-between land, half forest, half open plain, something ancient hesitates. The body wants to drop back to all fours, but something else, something small and persistent, keeps it standing. The question echoes through 6 million years of time. Why did one ape stand when every instinct said stay low? Around 7 million years ago, in what is now the Sahel region of Chad, a skull settled into the dust. It belonged to a species later called Sahelanthropus chadensis, the earliest known member of the human line. The fossil is incomplete, weathered by time, yet one small detail of its anatomy changed everything. The hole where the spine enters the skull, the foramen magnum, sits more forward than in other apes. That position suggests that the head balanced atop the spine instead of projecting forward from it. It means this being, whatever else it was, likely carried its head upright. That subtle shift in posture marks the first faint signal of what would become our defining trait, bipedalism. The world that Sahelanthropus inhabited was a mosaic, a patchwork of forested groves, riverbanks, and open grassland under shifting skies. Climate records drawn from fossil pollen and isotopes in ancient soils tell us the African continent was in flux. Monsoons came and went. Forest belts expanded and then collapsed again. For creatures adapted to life in trees, the ground was no longer something to cross. It was something to use. Standing upright was not a leap of invention, but a slow rebalancing between two worlds, the memory of the canopy and the necessity of the earth. 1 million years later, another early hominin appeared in the highlands of Kenya. Aurorin tuganensis, known from only a handful of fossils, bits of femur, teeth and jaw, walked the same uneasy border between forest and savanna. Its femur tells a clearer story than any skull. The shape of the femoral head and the thickness of the bone along its upper shaft reveal how it carried weight. It was not fully human, but it bore its mass differently from chimpanzees. The joint rotated inward and downward, an adaptation for supporting the body in an upright stance. Where Sahelanthropus hinted at upright posture, Aurorin practiced it. The landscape that demanded this change was unstable and capricious. The East African rift was widening, mountains rising, lakes forming and vanishing. These geological shifts fractured habitats and forced populations to adapt to new ecological mosaics. Fossilized plant remains and the enamel chemistry of herbivores from that time tell us that dense forests were giving way to mixed woodland. The canopy was no longer continuous. For primates used to the vertical security of trees, survival meant moving between food patches spread across broken terrain. 2 legs, it turned out, were an efficient way to do that. Standing upright is not only about walking, it is about energy. When a 4-legged animal moves, each step lifts and drops the entire body, wasting energy on vertical motion. Bipedal walking, though slower, is more economical over distance. A straight spine and arched foot convert gravity into momentum. Over a long day of foraging, an upright walker burns less energy and loses less water. In an environment that alternated between abundance and scarcity, efficiency became its own kind of intelligence. Another 2 million years passed before the most famous of these early upright forms emerged, Ardipithecus ramidus. Found in the Afar region of Ethiopia, Ardi as she's known lived about 4.5 million years ago. She was small, maybe just over 1 metre tall with long arms and a grasping big toe for climbing, but her pelvis tells a different story. It was short and broad, reshaped to support the torso directly over the legs. The top half of the pelvis resembled that of later humans, while the lower half retained the flexibility of a climber. Ardi was not leaving the trees. She was splitting her time between them and the ground. Hers was a life of dual citizenship between worlds. This compromise between forest agility and terrestrial balance shows how gradual the transition really was. For millions of years, evolution did not replace one form with another. It blended them. Ardipithecus could climb with grace, walk with effort, and survive in both shaded groves and open clearings. Her environment was neither the dense jungle of her ancestors nor the endless grassland that would later dominate the African horizon. It was an ecological patchwork, shaped by rivers, woodlands, and seasonal rain. Standing upright was not a revolution but a negotiation. Scientists have debated for decades what specific pressures drove these species to walk on 2 legs. Some suggest it began as a feeding posture, standing to reach fruit or to free the hands for gathering. Others argue it arose from thermoregulation. Standing exposes less of the body to the midday sun and more to the cooling breeze. Still others point to the need to carry food or infants across open ground. Each hypothesis captures a fragment of truth, and together they form a pattern. In unstable climates, flexibility itself was survival. The body that could do more things in more places would win the slow lottery of evolution. When we look at the bones of Ardipithecus, we are not just seeing a creature that stood. We are seeing an organism learning to adapt in time. The foramen magnum, the pelvis, and the femur all tell a story of compromise. Nature was reshaping anatomy one ligament at a time, testing balance and endurance. Fossil footprints of other animals at Ardi's sites, monkeys, antelopes, and elephants, show the mixture of habitats she navigated. Some prints were left in forest mud, others on open floodplains. She lived on a shifting map, her behaviour as fluid as the climate that surrounded her. The shift toward bipedalism also altered perception. When a primate rises even 1 metre higher, the horizon expands dramatically. Seeing farther means anticipating danger, spotting food, and reading the movements of others. Upright posture may have rewired attention itself, turning spatial awareness into forward planning. In the open landscape, eyes once tuned to the green distances of trees began to measure the blue line of the sky. In that subtle shift of perspective lay the beginnings of our long obsession with what lies beyond the visible. To the scientists who study these fossils, each bone carries a mixture of humility and awe. They are not perfect transitions. There are gaps, contradictions, and uncertainties. The skeleton of Sahelanthropus is still debated. Some argue it was not bipedal at all. Orrorin is known from fragments so small that entire debates hinge on a single groove in the bone. Ardipithecus itself is an anatomical puzzle that required years of reconstruction to understand. Yet altogether, they whisper the same direction of change, a lineage moving from vertical trunks to vertical posture, guided by the restless climate of the African Rift. The late Miocene and early Pliocene were ages of volatility. Dust cores from the Atlantic Ocean, record pulses of aridity sweeping out of Africa, interspersed with wetter intervals that allowed forests to regrow. Each cycle reshuffled the evolutionary deck. When forests expanded, arboreal forms thrived. When they collapsed, only the adaptable survived. These oscillations shaped not only body form but mindset. Each generation learned to live with uncertainty, to move when conditions shifted, to balance between worlds. This perhaps was the earliest inheritance of human behaviour, the instinct to adapt preemptively, to stand when the world changes. There is a quiet irony here. Standing upright made our ancestors more visible to predators. It slowed them down and exposed their silhouettes against the savannah light. Yet the benefit outweighed the risk. The freed hands, the expanded vision, and the efficient gait created a new niche, one that favoured endurance, cooperation, and awareness. Evolution's most enduring successes often begin as small inefficiencies that find new purpose. If we could watch one of these early hominins crossing a clearing, we might not notice the historic importance of the moment. The stride would be awkward, the posture not yet fully erect. Every step would be a compromise between instinct and necessity. But in those hesitant movements, evolution was solving a problem it had never faced before: how to survive when the ground replaces the branch. And so, over 3 million years, the forest dwellers of Africa began to walk. Not because they wanted to, not because they were destined to, but because the world around them kept changing. Standing up was simply the most efficient way to stay alive in a landscape that refused to hold still. When we stand today, we carry that memory in our bones, the long unbroken experiment of balance that began with Sahelanthropus, matured with Orrorin, and was refined by Ardipithecus. To rise against gravity is to repeat the gesture that first separated us from the forest floor. Every step we take on two legs is a continuation of that ancient decision to adapt rather than surrender. Soft volcanic ash, still warm from an eruption, and across it, the footsteps of a small family walking together. The prints are deep where the ground was wet, lighter where it had begun to dry, spaced in a rhythm that only a living being could have made. They move in parallel, side by side, two adults and perhaps a child, walking on 2 feet through a prehistoric silence. The wind covers their scent. The sky is heavy with ash. They will never know that in a few million years their path will be rediscovered, and their story read not from bones, but from the dust beneath them. What story do footsteps tell when the walker is long gone? Around 3.5 million years ago, in what is now northern Tanzania, a light rain fell on the slopes of a restless volcano. The volcano, called Sadaman, had blanketed the surrounding landscape with fine ash, forming a smooth grey carpet. As the rain mixed with this ash, it hardened into a kind of natural cement. Across that surface walked a group of Australopithecus afarensis, our distant relatives, neither fully ape nor yet human. Their footprints, preserved by time and chance, remain one of the most intimate records of our deep past. For centuries, scientists searched for the physical evidence of how early hominins moved, and then in the year 1978, at a site called 𝐓𝐈𝐌𝐿𝐄𝐒, paleoanthropologist Mary Leakey and her team brushed the dust from history's most delicate trail. The prints stretched for almost 30 metres, over 80 steps carved into solidified ash. Each print revealed a flat heel, a rounded arch, and aligned toes. features unmistakably belonging to a bipedal walker. They were not side prints from a crawling ape, not drag marks, not chance. They were the direct signatures of two-legged life. The species behind them, Australopithecus afarensis, is known from fossils found across East Africa, most famously from the skeleton nicknamed Lucy, discovered a few years earlier in Ethiopia's Awash Valley. Lucy's bones, dated to roughly the same time as the Letuli trackway, gave physical form to what those footprints implied. She was small, standing just over a metre tall, with long arms suited for climbing and legs adapted for walking. Her pelvis was broad, her knees angled inward, her spine curved to balance her weight over her feet. Together, Lucy and the Letuli prints told a story of evolution not through theory, but through evidence imprinted in stone. Each print in the Letuli trail measures about 20 centimetres in length. The spacing between them suggests a slow, measured pace, not a sprint or a panic. The stride length and depth variations reveal something even more profound. One individual was slightly smaller, one slightly larger, and a third, whose prints overlay the others in part, may have been a juvenile. It is not proof, but many scientists see in it the trace of a family group. The image that forms is almost cinematic, a small child walking in the steps of an elder, two adults keeping pace through the ash-laden morning. In that moment, millions of years before language or fire, a social bond was already being written into the ground. The Letuli prints also speak to biomechanics. When analysed under modern 3D imaging, the pressure distribution reveals a gait remarkably similar to our own. The heel strikes first, weight rolls along the arch, and the toes push off, an elegant transfer of energy unique to habitual bipeds. The big toe is aligned with the others, not splayed outward for grasping. This detail alone separates Australopithecus afarensis from the apes that still lived in the trees. Their walk was not a temporary behaviour. It was the new normal. The world Lucy and her kin inhabited was one of contrasts. Fossilised plant remains and animal bones from Letuli show a landscape of mixed grassland and woodland, dotted with acacia trees and seasonal lakes. Herds of grazing animals wandered nearby, ancient relatives of antelope, horses and elephants. Predators stalked them too, saber-toothed cats, crocodiles, and hyenas older than any known to history. In that environment, walking on two legs was not a luxury. It was survival. Bipedalism freed the hands to carry food or offspring and allowed the eyes to scan above the grass for danger. It conserved energy across long distances, and perhaps most importantly, it made movement more predictable in the unpredictable world. Yet Australopithecus afarensis was no modern human. Lucy's long arms and curved fingers remind us that the trees were still part of her life. She likely climbed to sleep or to escape predators. Her brain was only about the size of a chimpanzee's, around 400 cubic centimetres. But brain size alone does not measure intelligence. Behaviour does. The Letuli prints show coordination and confidence, a shared path through danger, a trace of awareness that goes beyond instinct. When you look at the footprints, there is something hauntingly familiar about their rhythm. The left-right cadence, the spacing, even the slight inward rotation of the feet resemble how we move today. It is easy to imagine the sound of those steps, the soft crunch of damp ash, the whisper of a breeze, the distant rumble of volcanic life. These were not random impressions. They were a moment of motion caught forever. The walkers left the scene unaware that the ground beneath them would solidify, that wind would later cover it, and that time would turn it into rock. They could not know that one day other primates would study those steps as evidence of their own becoming. Fossil evidence of Australopithecus afarensis has since revealed much about how this species lived. The pelvis and femur of Lucy indicate that her gait was not only upright but efficient. Her hip muscles were configured to stabilise her body with each step, preventing side-to-side sway. Her knees locked slightly during walking, a feature that allows humans to stand for long periods without fatigue. Every part of her anatomy, from the curvature of her spine to the angle of her ankle bones, testifies to a body built to live on two legs. What remains extraordinary is how early and how fully this adaptation appeared. The Laetoli footprints predate the use of tools, fire, or complex communication. Before art, before language, before everything that defines us, there was walking. Walking was the first technology of the mind, the act of planning a route, of trusting the next step, of connecting distant resources through movement. It was also the first thread of culture. Moving together implies coordination and care. The pace of a group must adjust to the slowest among them. That simple fact, matching steps, may have been the foundation of empathy. The social world of Australopithecus afarensis is difficult to reconstruct, but fossil sites like Hadar, where multiple individuals are found together, hint at group living. These early hominins likely foraged collectively, sharing food sources and warning each other of predators. The ability to walk in groups, to travel as a unit, expanded their ecological reach. A walking species could follow the seasons, explore new valleys, and survive droughts that might have wiped out those bound to a single habitat. The Laetoli trackway also captures a brief intersection of time and chance, an eruption, a rainfall, a walk, and preservation. Most evidence of life vanishes without a trace. Footprints are among the most fragile records imaginable, yet here they endured for over 3 million years. Their survival reminds us that history is not always written in grand monuments, but in the smallest marks left by ordinary movement. If you could stand at Laetoli today, the footprints would seem humble, shallow depressions in ancient tuff. But under the right light, they come alive. The curve of each arch, the faint outline of toes, the slight difference in depth between left and right, these are the closest we have to shaking hands with the past. When Mary Leakey first uncovered them, she reportedly fell silent, realizing she was looking not at an artifact but at a gesture, the moment life became aware of distance. These prints also remind us that evolution is not a ladder but a path, one that occasionally doubles back or fades. Australopithecus afarensis did not know it was paving the way for others. Its lineage would branch, some ending in extinction, others leading toward the genus that would later call itself human. But on that morning, with ash beneath their feet and danger all around, none of that mattered. All that mattered was the next step. Perhaps that is why those footprints still resonate so deeply. They are not just evidence of locomotion, but of continuity. The same rhythm that carried Lucy's kind across the Rift Valley still carries us across city pavements and mountain trails. The same coordination of muscles, balance, and trust that moved her body moves ours. To walk is to echo her memory. The footprints in the ash are not a fossilized past. They are a living inheritance. Every time we stand, we replay that ancient balance between gravity and will, between risk and direction. The Laetoli trackway is proof that long before we learn to build, to write, or to dream, we learn to move forward together. Imagine this. The sky itself begins to change. Seasons stretch and contract. The sun's path drifts slightly each year, and rainfall no longer obeys the rules of memory. The world grows colder, not suddenly, but relentlessly, and what was once a forest thick with fruit becomes a restless grassy plain. 3 million years ago, the Earth entered a rhythm of extremes. Ice grew in the north, deserts expanded in the south, and in Africa, where our ancestors walked, climate became a teacher that rewarded only one trait: adaptability. Could a changing sky be the first teacher? During the Pliocene epoch, the Earth began a long slide toward the ice ages. For tens of millions of years, global climates have been warm and relatively stable, but subtle astronomical forces known as Milankovitch cycles were now at work. The planet's orbit around the Sun is not constant. It stretches and tightens over time, the angle of its axis wobbles, and the direction of that tilt slowly drifts. These cycles unfold over tens and hundreds of thousands of years, changing how sunlight is distributed across the globe. The result is a shifting pattern of monsoons, rainfall and temperature, a planetary heartbeat that pulses through deep time. In Africa, this heartbeat translated into instability. Sediment layers in ancient lake beds like those in the East African Rift Valley preserve the record in exquisite detail. Geologists can read those layers like pages in a diary, each telling of ancient floods, droughts and winds. Around 3 million years ago, those pages begin to alternate rapidly between wet and dry conditions. The forests that had sustained earlier hominins gave way to a patchwork of woodland, grassland and scrub. The continent became a mosaic of shifting habitats. For a species that still depended on fruit, shade and water, this was both crisis and opportunity. The cooling of the Earth did more than reshape landscapes, it reshaped minds. The apes that had once known only one kind of environment now had to navigate many. Lakes appeared and vanished within generations. Rivers changed course. New predators arrived on the plains and familiar trees stopped bearing fruit. Survival meant predicting patterns, remembering locations, and improvising solutions. Evolution began to favour not the strongest or the fastest, but the most flexible, the ones capable of learning anew each time the climate rewrote the rules. Fossil evidence shows that during this period, the brains of hominins began to expand. Australopithecus afarensis, the same species that left the letter-life footprints, had a cranial capacity of roughly 400 cubic centimetres, similar to a chimpanzee's. But by 2.5 million years ago, later Australopithecines and early members of the genus Homo would exceed 500. That growth was not sudden. It was sculpted by volatility itself. As the environment became unpredictable, the neural architecture of memory, planning, and social cooperation gained an evolutionary advantage. Climate instability acts on behaviour in subtle ways. A consistent environment breeds specialisation. Animals evolve to exploit one niche perfectly. But when the environment swings between extremes, specialisation becomes a liability. In Africa's fluctuating Pliocene landscapes, generalists thrived. Those who could shift their diet, adjust their travel routes, or experiment with new foraging strategies had the edge. The brain became not just a control centre for movement, but a dynamic tool for adaptation. Every drought was a test, every flood a rehearsal. Geological cores from the ocean floor near Africa reveal layers rich in dust blown from the continent during dry phases. These dusty intervals correspond with key transitions in human evolution. As vegetation receded, the open grasslands favoured species capable of walking long distances and tracking widely dispersed resources. This meant not just stronger legs, but more complex minds. The brain had to integrate spatial memory, where the last watering hole was, which trees still bore fruit, how to navigate between them. In a sense, climate created cognition by forcing the mind to hold a map. The African rift, stretching from Ethiopia to Malawi, became both crucible and corridor for this transformation. Tectonic activity fractured the landscape into lakes, valleys and highlands, each with its own microclimate. Populations were often isolated by geography, then reconnected when conditions changed. Genetic diversity increased. Isolation encouraged adaptation. Reconnection spread innovations. Over millions of years, this rhythm of separation and reunion acted like an evolutionary pump, driving complexity in both genes and behaviour. The evidence for this comes not only from fossils, but from chemistry. The ratio of oxygen isotopes in ancient shells and soil carbonates records the waxing and waning of rainfall. In East Africa, these records reveal cycles of wet and dry that match the pacing of the orbital change. When the Earth's tilt increased, summers grew hotter and monsoons stronger, forests advanced. When tilt decreased, the rains weakened, deserts spread, and only the adaptable survived. Across these cycles, our ancestors learned, without knowing it, to cope with impermanence. To live in a world that changes this often is to live in a world that demands foresight. It was no longer enough to respond to immediate hunger or danger. The next season might not resemble the last. Those who could anticipate, who could imagine what might happen next, stood a better chance. This is how climate may have sculpted the brain. Not through direct selection for intelligence, but through selection for flexibility. The line between weather and thought is thinner than we think. At the same time, the expansion of grasslands brought new ecological relationships. Herds of grazing animals multiplied, and predators followed them. Early hominins, now spending more time on the ground, had to read these patterns, the movement of herds, the calls of birds signalling predators, the colour of the sky before a storm. Their survival depended on attention. Over time, attention itself became a form of intelligence, honed by necessity into awareness. Paleoanthropologists sometimes describe this shift as the transition from reactive to proactive cognition. In stable environments, animals react. In unstable ones, they plan. Around 3 million years ago, hominins crossed that threshold. Their brains did not simply grow, they reorganized. The regions associated with social behavior and spatial awareness expanded. The eyes moved slightly forward. The hands became more coordinated, and the face began to lose the heavy musculature of earlier apes, perhaps because communication and cooperation were taking on new importance. It is humbling to think that the seeds of curiosity were sown by drought. Every uncertain season asked a new question, and survival meant answering it differently each time. What does one eat when the trees stop fruiting? Where does one find water when the lake dries? How does one stay safe when the landscape itself becomes unfamiliar? Each of these challenges demanded not instinct but improvisation. And improvisation, repeated over millions of years, becomes imagination. Some scientists refer to this evolutionary pattern as the variability selection hypothesis, the idea that fluctuating climates, rather than any single environment, drove the evolution of human adaptability. In this view, intelligence is not a luxury of stability but a response to chaos. Our ancestors did not become smart because they lived in a rich environment. They became smart because their environment kept changing. The mind evolved as a buffer against uncertainty, a way of surviving a planet that refused to stay still. The fossil sites that record this story, Hadaz, Turkana, Olduvai, Homo, lie within what geologists call the East African Rift System, a region that remains geologically active even today. Lakes fill and vanish, volcanoes rise and erode. To walk across that landscape is to step through layers of time. Within those sediments lie traces of shifting vegetation, fossilized pollen, silica from grasses, charred wood from ancient fires. Each layer marks an experiment in survival. In that unstable world, evolution discovered a new kind of stability, the one found inside the skull. A mind that could adapt to many environments no longer depended on any single one. The brain became a portable habitat, carrying memory, strategy, and cooperation wherever its owner went. From that moment on, survival would depend less on the constancy of the world and more on the constancy of thought. The climate of the Pliocene did not only sculpt landscapes, it sculpted awareness. A cooler, drier, more unpredictable planet forged the neural foundations for curiosity, planning, and empathy. The same cycles that carved valleys and dried lakes also carved the pathways of the mind. And yet, the record reminds us how fragile this balance was. For every lineage that adapted, many vanished. Intelligence was not inevitable. It was conditional. If Africa had remained stable, perhaps the forests would have endured, and bipedal apes would have stayed small and specialised. But the Earth turned, the orbit shifted, and the sky began to teach. Every gust of wind, every drought, every flood wrote a new lesson in the history of the brain: to move, to remember, to adapt. The climate was not the backdrop of human evolution. It was the author. The echo of two stones meeting for the first time, sharp, deliberate and louder than it should be in a world still ruled by instinct. A hand lifts, strikes again, and a spark of purpose cuts through the noise of wind and scavengers. Flakes scatter like glass under the sun. The hand pauses, studies what it has made, and for the first time in 3 million years of walking and waiting, a living being understands that the world can be reshaped. What changes inside a mind that first strikes stone against stone? Around 2.5 million years ago, something quiet but revolutionary began to happen on the African plains. Fossil layers in the Great Rift Valley, in places like Olduvai Gorge in Tanzania and the shores of Lake Turkana in Kenya, preserve a record of early humans not just surviving, but creating. Mixed among ancient bones and river sediments are stones that have been deliberately chipped, fractured and reshaped. These are the oldest tools we know of, part of what archaeologists call the Older One industry, and with them comes the dawn of the genus Homo and the first known craftsman, Homo habilis, the handy human. Homo habilis was small by our standards, rarely exceeding 1.5 meters in height, with long arms and a slightly projecting face. But inside its skull, something new had begun to grow. A brain averaging 600 cubic centimeters, roughly 50% larger than that of its Australopithecine ancestors. The expansion itself was not the miracle. The miracle was how it was used. For the first time, thought began to loop through the hand. The brain did not simply move fingers, it listened to them. Each strike of stone against stone sent vibrations through the skin, signals through the nerves, and feedback through the mind. Creation had become a sensory circuit. The tools themselves were simple but effective, sharp-edged flakes and unrefined cores used for cutting, scraping and pounding. They were not made for beauty but for survival. When examined closely, the flakes show patterns of percussion, angles and scars that can only be made by intentional blows. These were not accidental fractures, they were acts of planning. The maker had to choose a suitable rock, understand how it would break, and predict where the next strike should fall. In that motion, we find the first evidence of foresight, the idea that effort now could yield reward later. Why did this begin then? The answer lies again in the changing world. Africa at this time was an unpredictable mix of dry grasslands and patchy woodlands. Herbivore herds were growing larger, and carnivores were fierce competitors. Early humans were not hunters yet, but they were opportunists. When lions or hyenas abandoned a kill, these small primates approached cautiously, tools in hand, and claimed what was left. A sharp flake could slice through hide or tendon. A heavy core could shatter bone to reveal the rich marrow within. That marrow, dense with fat and energy, became one of the most valuable resources on the savannah. Each successful strike on stone therefore represented not just ingenuity but survival. Breaking open bone was like breaking open time itself, a way of reaching nutrients that no claw or tooth could access. Over generations, the brains of those who used tools began to adapt to the precision required. The thumb's musculature grew stronger, the wrist more flexible, the fingertips more sensitive. Fossil hand bones of Homo habilis show a distinctive combination of strength and fine control. The species' very name reflects this, habilis, meaning able, skillful or handy. The making of tools also changed how early humans saw the world. Every object became potential. Stones were no longer just stones. They were edges waiting to happen. Bones were not carcasses, but containers. This shift from seeing to interpreting is the foundation of cognition. It suggests a mental leap from what is to what could be. For the first time, the natural world became raw material for imagination. Archaeologists studying Aldewan sites often find clusters of flakes, hammerstones, and bones scattered together. Small stations of activity where early humans worked, ate, and perhaps shared food. The spatial arrangement implies social behaviour. Toolmaking may have been learned through observation, imitation, and practice, skills that depend on communication. A young individual watching an elder strike stone might copy the motion, fail, try again, and eventually learn. Each attempt strengthened not only muscles, but memory. The rhythm of napping became a form of early language, sound as signal, repetition as instruction. It is easy to overlook how complex this act really was. To make an effective Aldewan flake, one must understand two things that are invisible: the internal structure of the stone and the angle of force. Every successful strike requires predicting how energy will travel through matter, a primitive form of physics, practiced long before anyone could name it. This suggests that Homo habilis was not only responding to its environment, but experimenting with it. Evolution had produced an animal that learned not just from experience but from the attempt itself. And yet, for all its innovation, this new way of life was still precarious. The savannah was full of predators faster, stronger, and more specialized than these early humans. Their survival depended on vigilance and cooperation. Studies of modern primates help us imagine their behavior. Groups of 5 to 10 individuals sharing territory, moving together between water sources. Tool sites near lakes and rivers suggest that Homo habilis returned repeatedly to familiar places, not aimlessly wandering, but mapping the land mentally. That mapping was an early form of abstract thought. To remember where food had been found before is to form a concept of time and space. The neurological cost of all this was immense. Brains consume energy, and for Homo habilis this meant a growing dependence on nutrient-rich food sources. Bone marrow, brain tissue from scavenged carcasses, and tough plant tubers all provided the calories required to fuel cognition. With every generation, those who could think more efficiently gained a subtle but decisive edge. Intelligence did not arrive all at once. It accumulated like flint dust at the bottom of a toolmaker's camp. Holding a stone tool, even in imagination, connects us across time. The edges are still sharp after 2 million years. Each flake fits naturally in the hand, shaped by the same proportions of bone and muscle that we carry today. If you turn it over in your palm, you can see where the maker struck. The point of percussion, the ripple lines of impact, the smooth surface of intent. You can almost feel the rhythm of ancient concentration, the silence between blows, the faint exhalation of effort. Neuroscientists today see in toolmaking the beginnings of what we call embodied cognition. The idea that thought is not confined to the brain but extends through the body and its interactions with the world. The coordination required to strike stone against stone, to anticipate the next movement, and to evaluate success in real time would have created neural pathways linking motor control, vision, and memory. Every flake chipped away not only refined the tool, but rewired the mind. It is likely that this craft also reshaped social life. The ability to create something transferable, a tool that could be given, shared, or shown, introduced a new layer of interaction. Cooperation could now be physical, not just emotional. A sharp flake could be passed between individuals, turning knowledge into object. This was the beginning of culture, not as art or language, but as technology, an inherited habit that outlived the body. Archaeological evidence shows that Aldewan tools remained remarkably consistent for over 1 million years. Their design was simple, their purpose universal, but the simplicity is deceptive. It implies a perfection of function that needed no improvement, and a cultural tradition stable enough to pass unchanged across generations. Teaching, imitation, and shared memory must already have been deeply ingrained. When viewed against the long timeline of life, this innovation is staggering. For over 3 billion years, evolution shaped creatures to fit their environments. With the first tool, a creature began to shape the environment instead. That moment, whether at Olduvai Gorge, at Gona in Ethiopia, or along the banks of Lake Turkana, marks the crossing of a threshold. The hand became an instrument of intention, and the world ceased to be a fixed stage. It became editable. Standing there, 2.5 million years ago, a small band of humans with crude stone flakes changed the course of evolution not through strength, but through reflection. They discovered that the simplest action, a strike, could produce something entirely new, that the world could yield to design, that survival could be improved, not merely endured, and perhaps most quietly of all, they discovered patience. Toolmaking demands repetition, frustration, and precision. It requires envisioning an outcome before it exists. That is not just skill, it is imagination. The stone in the hand was not just a tool, it was the first mirror of the mind. We may never know who struck the first blow, or what thought crossed their mind when the sharp edge appeared. But in that instant, a pattern began that has never stopped. The transformation of knowledge into creation. Every hammer, chisel, and keyboard traces back to that first collision of curiosity and stone. What changes inside a mind that first strikes stone against stone? Perhaps nothing at first, only a sound. But over time, that sound became language, that rhythm became memory, and that spark became us. Imagine this, a horizon without end. The heat shimmers, the air hums with insects, and a line of small, upright figures moves steadily across the Rift Valley floor. They are not running from anything. They are running towards something, toward new valleys, new rivers, new possibilities. Bare feet slap against packed earth, hearts pacing with the rhythm of endurance, lungs open to a hotter sky. The species that once watched from the trees now strides beneath them, no longer bound by forest but by curiosity. How far can curiosity walk before it becomes destiny? Around 2 million years ago, a new kind of human appeared in Africa. Taller, leaner, and more purposeful than its predecessors. This was Homo erectus, the first true traveller of our lineage. The world it entered was one of transformation. Global cooling had continued since the Pliocene, spreading savannas and grasslands across much of Africa and beyond. The Rift Valley, a long fracture running through the eastern part of the continent, was both cradle and corridor, a geological highway where evolution unfolded under extremes of climate and terrain. Here, adaptation was not optional, it was the cost of existence. Fossils from sites such as 𝐓𝐈𝐌𝐿𝐿 in Kenya and Olduvai Gorge in Tanzania reveal the anatomy of a creature made for distance. Compared to the shorter, stockier Homo habilis, Homo erectus had longer legs, narrower hips, and a more efficient stride. Its pelvis was restructured for balance and stability during upright locomotion, its feet fully arched to store and release energy with every step. The arms shortened, reducing the swinging weight carried from its arboreal past. For the first time, a human body could cover great distances without exhaustion. Even the skull tells the same story. A larger brain, averaging 900 cubic centimetres, required more calories and a wider range of food sources. To sustain such an organ, Homo erectus had to move farther and think ahead. It was a hunter, a scavenger, and a wanderer, living in small cooperative bands that followed herds and watercourses across vast territories. Mobility became survival, and movement itself became intelligence. The secret of Homo erectus was endurance. Unlike most mammals, which overheat after a brief sprint, humans developed the ability to run for hours. We lost much of the thick body hair that trapped heat, and evolved an extraordinary density of sweat glands. Our ability to regulate temperature through perspiration allowed long pursuit under the sun, while other animals forced to pant for cooling would collapse from exhaustion. This adaptation turned the savanna into an open field of opportunity. The first humans became persistent hunters, not the fastest predators, but the most relentless. Picture the scene. A herd of antelope grazes under the midday sun. A small group of upright figures approaches quietly, forcing the animals to bolt. But the humans do not chase at full speed. They follow at a steady pace, tracking footprints, scent and movement across the plain. Each burst of flight drains the prey's energy while the humans keep theirs. Hours pass. The animal begins to overheat. When it finally stumbles, the hunters are still there, calm, patient, and breathing evenly. This strategy, simple and ancient, may have fed both the body and the mind. To track is to predict, to plan, to imagine where something unseen will appear. And imagination is the foundation of thought. The evidence for this style of life lies scattered in both fossils and tools. Sites like 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 in Kenya, where the nearly complete skeleton of the Turkana boy was found, show a tall adolescent male, almost modern in proportion, long-limbed, athletic, with a brain near 1,000 cubic centimetres. His bones bear the marks of growth plates still active, meaning he would have stood even taller as an adult. Nearby stone artefacts of the 𝐓𝐈𝐌𝐿𝐄𝐒 tradition, symmetrical hand axes and cleavers, suggest planning and symmetry, skills requiring both physical precision and conceptual design. These were not random strikes of stone, but deliberate creations shaped to fit a mental template. Around the same time, fossils discovered far beyond Africa, in Dmanisi, Georgia, dated to about 1,800,000 years ago, reveal Homo erectus, or its close relative already walking beyond its birthplace. The site contains the remains of multiple individuals and thousands of stone tools, along with animal bones bearing cut marks. These people had learned to survive in cooler climates, thousands of kilometres from the tropics. Their presence there marks the first known dispersal of humans out of Africa, a quiet preview of what would become a global story. But the origin of that journey remains rooted in the African Rift, where anatomy, behaviour and endurance first converged. The transformation of the human body during this time was as much about energy as motion. Walking upright on long legs reduced the metabolic cost of travel. Efficient running allowed the pursuit of distant resources and the exploration of new landscapes. A species that could move farther could also think farther, planning routes, remembering landmarks, and coordinating group efforts. Over generations, these pressures shaped not only physiology, but psychology. The brain began to specialize in anticipation. It became a traveler's mind, wired for distance, navigation, and shared purpose. The changes extended even to the face. The heavy jaws and protruding snouts of earlier hominins gave way to flatter profiles, allowing better balance of the head during motion. The external nose grew more pronounced, helping to humidify and cool air during long runs. The shoulders rotated more freely, enabling the throwing of stones or spears long before weapons existed. Every detail of the body spoke of movement. Homo erectus was no longer built to cling to trees or sit in shade. It was built to roam. In a sense, the Earth itself trained this species. The Rift Valley's tectonic forces created a geography of change, mountains rising, rivers cutting new paths, climates shifting across short distances. Population separated by these barriers evolved slightly differently, experimenting with forms of locomotion, diet, and social behaviour. The result was a dynamic equilibrium, diversity held together by mobility. Wherever the environment allowed, Homo erectus walked in, stayed a while, then moved on. For a moment in deep time, the planet was a classroom for endurance. To travel such distances, early humans had to rely on cooperation. A single individual could not carry enough water or meat for a journey. Groups had to communicate, coordinate, and share. That social bond may have been as important as any physical adaptation. Moving together meant watching over one another, protecting the young, carrying knowledge of where water and shelter could be found. The first shared memory was not a story told around fire. It was a route remembered across the landscape. The fossils from this period suggest that Homo erectus had also begun to master delayed gratification, the ability to work for future rewards. A hand axe could take time to make but last for many uses. A tracking pursuit might require hours of focus before the kill. This shift from immediacy to patience marks another leap in cognition. It indicates an understanding of cause and effect, of preparation and payoff. The mind was learning to project itself forward in time. Anatomically, the brain of Homo erectus was approaching that of early Homo sapiens in both size and organisation. Endocasts, natural moulds of the interior of skulls, show evidence of expanded frontal lobes, regions associated with planning, coordination, and problem-solving. Yet despite this increase, the faces of Homo erectus retained simplicity. No jewellery, no art, no symbols. Their sophistication lay in endurance, not expression. They mastered the physical world before the imagined one. Still, the leap was immense. Homo erectus achieved something no other species had done before. It made movement itself a survival strategy. Other animals adapted to one environment. Humans adapted to all by never staying still. This mobility meant that local disasters no longer spelled extinction. When drought struck, they could walk beyond it. When predators overhunted an area, they could move elsewhere. Their adaptability was not only biological, it was behavioural. They learned to live with change by following it. If you stood on the edge of the Rift Valley then, you might have seen them at dusk, small silhouettes crossing ridgelines, walking toward the glimmer of water far away. They would rest briefly, perhaps gnawing on scavenged meat or sharing the marrow of a bone cracked earlier in the day. There was no concept of destination, only direction. The horizon itself was their companion. The story of Homo erectus is not just one of movement across space but across time. Over the course of more than 1 million years, this species persisted through ice ages, droughts, and volcanic upheavals. It spread from Africa into Asia, leaving footprints in Georgia, Indonesia, and China. But its heart, the evolutionary workshop where its form and mind took shape, remained in the rift. There, under the African sun, endurance turned into destiny. Even today, traces of their design remain in us. Our ability to sweat, to run long distances, to balance on 2 legs with grace. These are gifts from the runners of the rift. Our restlessness too, the quiet urge to see what lies beyond the next hill, may be their most enduring legacy. Curiosity and distance became the twin engines of humanity. How far can curiosity walk before it becomes destiny? For Homo erectus, the answer was simple. As far as the world would allow. For the rest of us, still walking in their shadow, the journey has never really stopped. This, a night with no stars, only the endless dark of the African interior. The air is cool, the predators restless, and a group of early humans huddles in silence. Then, somewhere near the cave wall, something changes. A faint orange flicker, a pulse of warmth against the wind. A branch catches, cracks, and begins to glow. For the first time, the night does not win. The humans do not flee. They stay, watching, learning, waiting. It is not yet mastery, not yet comfort, just a fragile collaboration between chance and curiosity. But from that small trembling light, everything that would follow, memory, myth, civilization, begins to take shape. Around 1.5 million years ago, Africa and much of the world began to cool once more. Glacial cycles waxed and waned, forests thinned, and open habitats returned, dotted with caves and shelters that offered refuge from wind and cold. In this shifting world, Homo erectus, the same species that had conquered distance, faced new tests. The day belonged to endurance, but the night still belonged to fear. Fire changed that balance. The first traces of humanity's relationship with flame come not from a single discovery, but from scattered whispers in the geological record. Charred bones, reddened earth, pockets of ash embedded deep in ancient sediment. Some are ambiguous: lightning strikes, natural wildfires, volcanic residue. But a few stand apart, arranged and layered in ways that nature rarely produces on her own. Among the most famous lies deep inside Wonderwerk Cave, in the northern Cape of South Africa. Within its dark chambers, archaeologists found a thin seam of ash and burned bone fragments dated to about 1 million years ago. The microscopic structure of the ash tells a careful story. The wood had been burned at relatively low temperatures, around 600 degrees Celsius, and then cooled slowly, suggesting it smouldered in place rather than being swept in by flood or wind. The bones, too, were burned unevenly, as if they had been cooked or discarded near a fire rather than engulfed in one. To control fire even briefly required more than luck. It meant watching, tending, feeding, an act of patience and attention that pushed the mind outward in time. Fire was not just warmth, it was time made visible, a living process that responded to care and discipline. Too much wood and it roared out of control, too little and it died. To keep it alive through the night, someone had to stay awake. Fire demanded cooperation. It drew early humans together, not just physically, but cognitively. Shared vigilance, shared rhythm, shared protection. Those who mastered its pulse survived the cold, the dark, and the predators beyond the glow. In caves like Wonderwerk, 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 in Israel, and 𝐓𝐈𝐌𝐿𝐿 in Kenya, evidence suggests that these early fires were maintained intentionally rather than stumbled upon. Charred seeds and stones cracked by heat hint that fire was used not only for warmth or defense, but possibly for preparing food. Cooking transforms nutrition. Heat breaks down tough fibers, softens starch, and releases more calories per bite. Over generations, this could have driven a quiet revolution inside the body. Shorter intestines, smaller teeth, and more energy available to the growing brain. The cooking hypothesis, proposed by biological anthropologist Richard Wrangham, suggests that fire was the turning point that made large brains sustainable. Raw meat and roots require long digestion and yield limited energy. Cooked food does the work outside the body, freeing resources for neural expansion. It is a beautiful idea, though not yet proven, and one that fits the broader pattern of Homo erectus: energy efficiency, long-distance mobility, and a rising intelligence shaped by cooperation. Imagine the first moments of cooking, if that word can even apply. A carcass found after a wildfire, its flesh strangely tender, the scent drawing scavengers. A cautious taste, smoky, warm, unlike anything before. Slowly, over hundreds of generations, the association forms. Flame can change food, and change it for the better. Whether by accident or imitation, those who learned this secret had an advantage that multiplied over time. But perhaps the greatest transformation was not nutritional at all. Fire changed perception. It extended the day. Around its glow, faces became visible again after sunset, expressions legible, gestures meaningful. The flickering light created the first theatre. Shadows on stone, movement amplified, fear softened by familiarity. Predators that once ruled the night began to keep their distance. The boundary between day and darkness, once absolute, became negotiable. Humanity began to reclaim time from nature. With that extension of day came reflection. Fire may have been the first teacher of patience and abstraction. Watching embers die and flare, humans saw cause and effect in motion, a living demonstration of control. Sparks taught about transformation, wood into ash, light into heat, energy into safety. This pattern, repeated nightly, may have planted the earliest seeds of causal reasoning and ritual. To tend a flame is to predict the future in miniature. The act of gathering around fire also changed the rhythm of communication. Before, social interaction likely waned after dusk. After fire, conversation could continue. Quiet planning, teaching, or perhaps wordless comfort. Anthropologists suggest that this evening effect might have encouraged the evolution of complex language and storytelling. The flicker of light not only warmed the body but illuminated the mind. We can only guess what those early nights looked like. Perhaps small groups huddled close, each person feeding the flame with dry grass or sticks, learning by imitation. Sparks would rise, each one carrying a piece of their collective breath upward. The fire would hum, smoke curling into the ceiling of a cave, marking it black over centuries. To this day, the soot in 𝐓𝐈𝐌𝐄𝐒𝐒 still clings to those walls, a record of every night someone refused to let the dark return. Outside, the world was still dangerous. Glacial cycles pulsed across the continents, lowering sea levels and changing rainfall. Nights grew colder. Fire was not a luxury. It was survival. The glow became a moving hearth, portable when needed, stable when found. Archaeological hints suggest that these early fires were not confined to one site. Burned sediments appear across Kenya, China, and the Levant around the same time frame, implying that fire use spread gradually across populations. Whether this spread was through observation, imitation, or shared ancestry, we cannot yet say. But the rhythm is familiar. Once knowledge exists, it travels. Each group that discovered or adopted fire carried a spark of intelligence, literally, to the next. For the first time, humanity had found a tool that could multiply itself. It is easy now to see fire as inevitable, but for most of our prehistory, it remained a fragile skill. A single rainstorm could erase weeks of effort. A burned hand or out-of-control flame could breed fear and avoidance. Mastery likely came in stages. First opportunistic use of natural fires, then cautious maintenance of smouldering embers, and eventually, much later, deliberate ignition. In the period between 1.5 and 800,000 years ago, we stand somewhere in the middle, the age of learning to keep what nature gives. Perhaps that is why the traces in the record are so subtle. True fire-making leaves little behind. No bones or tools, just the faintest shadow of heat. And yet its impact rippled through every future adaptation. Fire enabled higher latitude survival, altered diets, expanded social networks, and provided protection that made rest possible. Even sleep itself may have evolved under its watch. Some researchers propose that fire's safety allowed deeper, more consolidated sleep cycles, freeing the mind for memory and dreaming. If true, then our ability to imagine might owe itself to a campfire that never went out. From a distance, a cave glowing in the dark must have seemed like a second sun, small, trembling, and alive. To the predators of the plains, it was an alien thing, a smell and sound not found anywhere else. To us, it was the first sign that nature had competition. The flicker of control had begun, but this new light came with a paradox. It made the night safe, and at the same time, it revealed it. Around the fire, shadows moved in ways the brain struggled to explain. Every sound beyond the ring of light became a question. Fire created imagination because it created mystery. To be human was now to live between light and dark, to look into the fire and wonder what lay beyond its reach. In this moment, the story of survival became the story of understanding. The same curiosity that once pushed Homo erectus across continents now pushed inward, toward the nature of matter, change, and permanence. A burning log taught transformation. A dying ember taught loss. Together, they formed the first curriculum of thought. If you could stand in 𝐓𝐈𝐌𝐾𝐒𝐒 today, quiet and still, you might see what they saw. the faint scorch of heat against the stone, the ghosts of hands that once tended the same flame. The air, even now, smells faintly of earth and ash. The fire they built there has been out for nearly 1,000,000 years, but in a way it never really ended. Every stove, every candle, every electric bulb is a continuation of that first act of defiance against the dark. What did the first controlled flame teach its watchers? That warmth could come from the cold, that danger could become safety, and that change could be guided, not feared. The light we carry now in every city, every screen, every restless thought, is their inheritance. Somewhere, deep in time, a spark still burns on the wall of a cave, waiting for us to remember what it meant to sit together in silence and see the night for the first time. Imagine this. Wind sweeping across an old lake bed, the air dry and thin. Nothing moves but the dust, a fine, invisible rain of time. That dust carries more than silt and ash. It carries fragments of bone, the faint trace of blood proteins, the mineral ghosts of teeth. Within those grains lies something smaller than sight but vast in meaning, the first whispers of our divided ancestry. Each particle a letter, each layer a line in a story that no one wrote, but everyone lived. For hundreds of thousands of years, Africa was not one homeland. It was a continent of experiments, a scattered mosaic of humans who would one day become us. Between 700,000 and 400,000 years ago, the African landscape was alive with flux. Forests shrinking, savannas spreading, deserts blooming and vanishing in endless cycles. Earth's orbital patterns, the slow pulse of the planet's tilt and orbit known as the 𝐓𝐈𝐌𝐄𝐒𝐓𝐀𝐌𝐏𝐒 cycles, orchestrated these shifts with mathematical precision. Each cycle stretched over tens of thousands of years, alternating between wet and dry, warm and cold. These environmental rhythms didn't just shape landscapes, they sculpted genes. Out of this climate choreography emerged a species we call Homo 𝐓𝐈𝐌𝐏𝐒𝐒, not quite us, not quite gone. The fossils first described in Europe, at a site near Heidelberg in Germany, gave the species its name. But its heart, its origin, beats in Africa. Sites like Bodo in Ethiopia, Kabwe in Zambia, and Cima de los Huesos in Spain preserve variations of the same adaptable form. The African populations were taller, more robust, with strong brow ridges and large brains averaging 1,200 cubic centimetres, a midpoint between Homo erectus and modern humans. Their faces were still heavy-boned, but inside their skulls the architecture of thought was expanding. The bones tell a story of continuity, an African lineage slowly refining the body and mind that would one day define Homo sapiens. Yet, the genes, recovered in trace amounts from sediments and fossilized fragments, whisper of something far more intricate. Ancient DNA, a field that seemed impossible just decades ago, now allows us to read what the dust preserved. Each fossil's surviving molecules, fragments of mitochondrial DNA, traces of nuclear code, reveal a pattern of divergence and convergence across continents. By 600,000 years ago, populations of Homo 𝐓𝐈𝐌𝐿𝐵𝐴 in Africa, Europe and Asia were beginning to drift apart genetically. Barriers of distance, climate and terrain limited their contact. Over thousands of generations, this isolation produced three major branches of humanity. One remained in Africa, carrying the seeds of what would become Homo sapiens. Another in Europe gradually developed the traits we would recognize as Neanderthal. The third, somewhere deep in Asia, gave rise to the Dinosaurs, a lineage we would not rediscover until fragments of their DNA emerged from a cave in Siberia almost 500,000 years later. The strange poetry of this time is that no one living then could have known these divisions existed. They were invisible, slow shifts in gene frequencies, tiny mutations passed from parent to child echoing across epochs. A population that lived beside a river in Zambia could have looked and acted much like one in Spain, unaware that their descendants would someday be classified as different species. Evolution works in silence, its signatures written into chromosomes long before bones show the change. At Bodo, in Ethiopia's Rift Valley, the skull of a Middle Pleistocene human shows the blend that defines this era. A broad, flat face and thick brow ridges of an earlier age, but with a cranial capacity approaching that of modern humans. Cut marks on the skull's surface suggest careful defleshing, perhaps part of a ritual or mortuary behaviour, the first hint that cognition and curiosity were turning toward mortality itself. In Zambia, the Kabwe skull, once called Broken Hill Man, preserves similar anatomy, though with even greater robustness. Together these finds map a species spread wide across Africa, unified by adaptability, but diversified by distance. Geochemistry helps fill in the blanks where fossils cannot speak. Isotopic analysis of tooth enamel and bone reveals ancient diets, a shifting balance between meat and plant, wetland and dry grassland. The variability is immense. Some 𝐓𝐈𝐌𝐿𝐵𝐴𝐿𝐵 populations lived by rivers, eating aquatic plants and fish. Others ranged across open savannas, hunting large mammals. This dietary flexibility mirrored their genetic diversity. Africa at the time was a patchwork of semi-isolated groups, each evolving under slightly different pressures. Modern population genetics still carries that imprint. Deep, regional structure within Africa far older than the species Homo sapiens itself. From the European line, we later see specialization into Neanderthals, short, stocky and cold adapted. From the Asian branch, the Denisovans emerge, mysterious and ghost-like, known more from genome than from skeleton. But from Africa, the trajectory bends differently. Instead of specialization, it favours versatility. The African populations faced not the uniform cold of glacial Europe, but constant fluctuation, alternating droughts and rains, forests and deserts. To survive such chaos required plasticity, not perfection. Flexibility became fitness. The African 𝐓𝐈𝐿𝐵𝐴𝐿𝐵 populations evolved brains not only larger but more adaptable, wired for uncertainty. It is possible that communication and cooperation deepened during this era. Evidence from sites like Katupan and Oloriazili shows refined Acheulean hand axes with balanced symmetry and consistent form, objects that imply teaching and shared technique. A stone perfectly shaped on both sides suggests a shared idea, a mental template held in multiple minds. In that sense, genes and culture were co-evolving. DNA diversified across space while knowledge circulated across time. Some researchers call Homo 𝐓𝐈𝐿𝐵𝐴𝐿𝐵 the last common ancestor, the species that stood at the crossroads before the human family split three ways. But the fossil record does not show a clean fork. It shows a braided river of inheritance. Populations merged, separated, and reconnected repeatedly, leaving overlapping signatures in both morphology and genome. When we say ancestor, what we mean is not an individual, but a network, a continent alive with connections that occasionally drifted apart. Ancient DNA from sediments has revolutionized this view. Even without full bones, soil samples from caves can contain the genetic dust of those who once lived there. Microscopic traces of sweat, hair, or skin filtered through millennia. These environmental genomes confirm that Neanderthals and Denisovans had already diverged from their African relatives by roughly 600,000 years ago. But even after that split, there were echoes of contact. Later genetic comparisons reveal that both of these Eurasian groups carried small fragments of DNA traceable back to even earlier African lineages. Evolution, it seems, never stopped crossing borders. In Africa itself, genetic studies of modern populations still reveal ancient divisions, evidence that humans never descended from a single Eve, but from multiple interacting populations that shared genes across vast distances. The continent was a living web, its deserts and forests serving as both barrier and bridge. Where climate pushed groups apart, curiosity pulled them back together. Every drought, every river shift, redrew the map of ancestry. One striking insight from isotope and fossil evidence is that Homo heidelbergensis likely migrated seasonally within Africa. The Rift Valley acted as a corridor linking resource zones, while changing lakes and grasslands created cycles of dispersal and reunion. This mobility prevented isolation from hardening into extinction. Instead, it maintained the genetic conversation that would, hundreds of thousands of years later, give rise to us. We can think of this time as the deep rehearsal of humanity. Brain size was already large, social cooperation was established, technology was consistent, endurance and adaptability were proven. Yet something still awaited ignition. Not fire this time, but reflection. These people had the capacity for language-like communication, though we cannot know how structured it was. They likely shared tasks, planned hunts, and taught their young through imitation. The intelligence was there. What remained was awareness, the ability to see the self in time. That spark would come later. If you could travel back to that world, you would find landscapes familiar yet uninhabited by any mind that would recognize you. The air would be rich with dust carrying spores, pollen, and invisible traces of DNA that would one day reveal their story. You might see small bands moving along a dry riverbed, tall, strong, laughing in voices we could not understand. You might not even realize they were your ancestors. Their genes are still in you, buried deep in the folds of your chromosomes, silent but enduring. The fossils of Homo heidelbergensis are heavy, their brow ridges thick, their faces wide. But their true legacy is lighter than dust. It lives in the chemical memory of soil, in the isotopic fingerprints of bones, and in the shared code still whispering in every cell of our bodies. These were the humans who bridged the gap between endurance and identity, the keepers of a genetic thread that would stretch through Neanderthals, Denisovans, and finally to us. How do fossils keep a record smaller than dust but larger than memory? By never truly disappearing. Their atoms move through time, their DNA survives in echoes, and their story continues, written not on stone tablets, but in the quiet spiral of every living human cell. A face emerging from the dust, familiar yet not. A brow less heavy, a skull more rounded, eyes deep and wide with recognition. You could almost mistake it for someone you know, until you remember it has been lying beneath Moroccan earth for 300,000 years. The features are neither ancient nor modern, neither primitive nor human in the way we mean it now. They are both. When does resemblance become ancestry? At what point does an echo turn into a voice? Around 400 to 300,000 years ago, something extraordinary was unfolding across Africa. It was not a single event, not a sudden birth of modernity, but a slow and scattered convergence. Populations across the continent, from Morocco to Ethiopia, from South Africa to the Rift Valley, were beginning to share a pattern of anatomy that feels uncannily familiar. These were not yet Homo sapiens as we know them, but they were on the edge of becoming so. The story of these people, the almost us, is one of mosaics, not revolutions. The most haunting of these early faces was unearthed at 𝐓𝐈𝐌𝐿𝐿, a rocky hillside in western Morocco. When miners first uncovered the fossils in the 1960s, they assumed they had found Neanderthals. The heavy brow ridges and robust skull seemed archaic, but radiometric dating would later change everything. Using thermoluminescence on the flint tools buried alongside the bones, scientists revealed their true age, roughly 300,000 years old, far older than any known Neanderthal, and far older than the first Homo sapiens fossils ever found. What emerged from that red sandstone was a paradox, a species that looked half ancient, half familiar, holding a mirror that reached both backward and forward in time. The skulls from 𝐓𝐈𝐌𝐿𝐿 show a curious blend of traits. The face is flat and delicate, with small cheekbones and a lightly built jaw, almost indistinguishable from a modern human. Yet the brain case is long and low, shaped more like that of an earlier species such as Homo heidelbergensis. This combination, modern face, archaic skull, is what scientists call a mosaic morphology. It suggests not a linear transition but a web of regional populations evolving in parallel, exchanging genes and ideas across Africa. The tools found at 𝐓𝐈𝐌𝐿 tell a similar story of transition. Flint flakes and points shaped by the Levallois technique, a more sophisticated method that requires pre-planning and spatial awareness, were scattered among animal bones bearing cut marks. These people hunted, butchered and shared meat, showing both skill and social coordination. But more telling than the tools or the bones is the pattern of continuity. The same style of tools appears across Africa around this time, in Kenya, Ethiopia and South Africa, suggesting not migration from one centre, but diffusion through many connected groups. Far to the south, another clue lies in Florisbad, near Bloemfontein. There, in 1932, a worker digging a spring uncovered a skull that puzzled anthropologists for decades. The Florisbad fossil, now dated to around 260,000 years ago, shares a similar mix of features: a modern-looking face attached to a thicker, archaic cranial vault. Its owner could easily walk unnoticed among us today, perhaps a bit broader, a bit tougher, but human all the same. The Florisbad skull reinforces the pattern seen at 𝐓𝐈𝐌𝐿. Humanity's emergence was not a single spark, but a slow, continent-wide glow. Different regions contributed different traits. Some populations developed lighter faces, others larger brains, others subtle changes in limb proportions or teeth. Over thousands of generations, these traits mingled, recombined and refined, until a species recognizable as Homo sapiens finally appeared. Africa was not one birthplace, but a network, a vast evolutionary workshop stretching from the Mediterranean to the Cape. In the east, along the Homo River in Ethiopia, another piece of this story rests in ancient sediments. At 𝐓𝐈𝐌𝐄𝐒𝐒, discovered in the 1960s and redated in recent years, scientists found two partial skulls that looked unmistakably human. Their age, about 230,000 years old, places them close to the moment when modern anatomy was nearing completion. The Homo fossils possess a high, rounded skull and smaller brow ridges, features considered hallmarks of our species. Yet, in subtle ways, they still carry the imprint of the past. The transition was not complete. Evolution rarely works in straight lines. Taken together, 𝐓𝐈𝐌𝐿, Florisbad, and 𝐓𝐈𝐿𝐄𝐒𝐒 rewrite the idea of a single cradle of humankind. Instead, they reveal something more dynamic, a Pan-African story. Populations separated by thousands of kilometres were evolving in parallel, exchanging genes when climate and migration allowed, diverging again when deserts or droughts intervened. Rather than a single origin point, there were many, small fires burning across a dark continent, each one contributing light to the whole. Recent studies in ancient DNA and population genetics support this view. Although no DNA has yet been extracted directly from fossils as old as 𝐓𝐈𝐌𝐿, the genetic diversity among modern Africans carries its signature. It suggests that early Homo sapiens were never one homogeneous group, but rather a collection of semi-connected populations that occasionally mixed. The African genome, even today, preserves traces of ancient sublineages, hints of forgotten human groups that may have vanished but left their essence in our blood. What makes this era fascinating is its ambiguity. The line between archaic and modern blurs until it becomes meaningless. The 𝐓𝐈𝐿𝐿 individuals were already using tools that required abstract thinking. The Florisbad person lived at a time when controlled fire was common, and organised hunting likely shaped daily life. The Homo humans stood on the threshold of symbolic behaviour, though we have yet to see their art or ritual. They were not almost human. They were already human, just not yet us. Their world was harsh, but not hopeless. Africa's ecosystems were fluctuating rapidly. Droughts followed by humid pulses, grasslands turning to deserts and back again. These changes forced adaptability. Populations moved, met, and mingled. The constant motion created what evolutionary biologist Eleanor Seri calls mosaic evolution. Not one linear transformation, but many local experiments merging over time. If evolution were drawn as a tree, the African one would look more like braided roots than a single trunk. One of the great philosophical implications of this view is that ancestry is not a point in space or time, it is a process. When we ask where humans began, the answer may be everywhere. We are the sum of countless lineages that met, mingled, and dissolved again in the great mixing bowl of Africa's deep past. The 𝐓𝐈𝐌𝐿 skulls are one face of that process, Florisbad another, Homo another still. Each is a portrait of humanity mid-thought, halfway between endurance and imagination. We can imagine their lives not as alien, but as continuous with our own. Small groups moving through seasonal landscapes, following rivers that have long since dried. Children learning to strike flint, laughter around embers, stories told without words. Their language, if it existed, might have been simple, but their curiosity was vast. When we look into the eyes reconstructed from these fossils, we recognize the same geometry of empathy, the same capacity to wonder. Archaeology, in its quiet way, has turned these bones into mirrors. They show us that being human is not about the sharpness of the jaw or the roundness of the skull. It is about the accumulation of variation, the layering of chance, the endless conversation between adaptation and imagination. The people of 𝐓𝐈𝐿, Florisbad, and 𝐓𝐻𝐒𝐒𝐌𝐏𝐻𝐒 were not stepping stones. They were chapters in a continuous autobiography that still has no ending. If you were to meet one of them on the savannah, face to face, you might hesitate before deciding who was more ancient. Their gaze would be steady, intelligent, perhaps curious about your strange clothes, but not frightened. In their expression you might see your own reflection, stretched across hundreds of millennia. You might even recognize something deeper. The quiet understanding that survival and meaning are the same thing. When does resemblance become ancestry? Perhaps at the moment when a face in the ground feels like family. These fossils are not relics of a vanished species. They are relatives we simply forgot to remember. Each one is a reminder that our story began not with a spark, but with a slow dawn. A continent waking to its own reflection. A circle of people under the faint glow of twilight, sitting silently as the fire breathes between them. No one speaks, not yet. There are no words for hunger or kinship or gratitude. But still, they know. One person passes a piece of red ochre to another, smearing pigment on a rock or a tool's handle. Perhaps as a sign, or maybe for beauty. We can't be sure. A third offers a shard of black volcanic glass, unlike anything found nearby. The gesture is deliberate, a gift, a connection. In the quiet before language, humanity was already learning to think together. Between 300,000 and 200,000 years ago, long before the first migration out of Africa, something invisible began to take form. A network. Across the continent, scattered groups of early Homo sapiens began to trade, share, and imitate, creating the faint but unmistakable structure of society. They did not have villages or nations, not even tribes as we understand them. What they had was something subtler, cooperation woven through time and distance. The evidence lies not in texts or monuments, but in stones and colours. At sites like 𝐓𝐈𝐌𝐿𝐿 in Kenya's Rift Valley, archaeologists have found pieces of obsidian, volcanic glass so sharp it fractures at the molecular level. What makes these finds remarkable is not the material itself, but where it came from. The same obsidian appears in layers more than 50 kilometers apart, carried by hands that must have known its value. Across the rift, this pattern repeats. The glass was not random debris, it was moving, traded, gifted, or exchanged through generations. This movement suggests more than practical trade. Obsidian is beautiful, dark, reflective, almost supernatural when struck by light. To carry it across the landscape, to exchange it for something unseen, means that people already understood the idea of shared worth. They recognized beauty, rarity, and reciprocity. These are the beginnings of symbolic thinking, not yet language, but meaning. Around the same time, pigments begin to appear in archaeological layers across Africa, at sites such as Twin Rivers in Zambia, Cap Thurin in Kenya, and the famous Blombos cave precursor levels in South Africa. Lumps of red ochre, iron-rich clay, were collected, ground, and sometimes scraped into powder. Red is not a colour easily ignored. In nature, it marks danger, blood, and life. To use it deliberately is to understand its power. Whether these early humans painted their bodies, decorated tools, or marked surfaces, we cannot say for certain. But the act itself, taking colour from earth and applying it to the world, was a quiet declaration. The environment was no longer just lived in, it was interpreted. Pigments suggest communication, not words but signs that meant something to those who shared them. A red mark on a stone, a smear on skin, a line on a tool handle, these might have identified individuals, groups, or achievements. They might have been used in rituals we will never reconstruct. In every case, they reveal minds thinking beyond survival. The brain had begun to use abstraction as a social tool. Another piece of this puzzle glints in the archaeological record. Ostrich eggshell beads. Found at sites across eastern and southern Africa, these tiny ornaments date to around 250,000 years ago, though similar objects appear even earlier as raw fragments. Drilled, polished, and often grouped in strings, they are among the first personal adornments in human history. Each one takes patience. A small circular hole scraped by stone, the edges smoothed with sand, the whole piece shaped into symmetry. Such objects serve little practical purpose. They are pure expression, symbols worn to say, I am part of this. What these beads represent is nothing less than the birth of social identity. In a world without names, a bead was a word. A necklace might have marked belonging, trust, or shared ancestry. Even if language existed only in fragments, these objects spoke fluently through form and pattern. To craft such items and share them implies more than skill. It implies recognition of self and others, of group and individual. This growing web of connection was not limited to ornament. It extended across landscapes. Obsidian travelled north to south, ochre east to west. The Rift Valley became a kind of prehistoric highway, a corridor linking environments and cultures. Genetic models suggest that populations across Africa were not isolated tribes but fluid groups that sometimes merged, sometimes drifted apart, exchanging both genes and ideas. Every trade, every gift carried information. Where water could be found, which plants healed, which stones cut cleanest. In sharing, they were inventing continuity, the slow, invisible fabric of culture. The act of exchange itself may have been the first social ritual. To hand over an object implies trust. To receive it implies understanding. Even before words, this was a dialogue, one that required memory and expectation. When a group met another, the exchange of materials likely carried rules, generosity, respect, perhaps the subtle dance of alliances. Archaeologists have observed that traded materials often travel in predictable patterns, suggesting stable routes and repeated contact. That kind of consistency does not emerge by chance. It requires organisation, teaching, and shared norms. Think of what this meant for cognition. A hunter who found a rare stone in the mountains and carried it hundreds of kilometres had to remember not just the stone's source, but its social context. Who wanted it? Who would value it? What it was worth in return. This memory web demanded imagination. The human mind was beginning to operate on unseen relationships, connecting not just objects, but intentions. It's easy to underestimate how radical that shift was. For millions of years, survival had depended on direct action: eat, flee, mate, rest. But by 300,000 years ago, survival increasingly depended on understanding others, predicting behaviour, negotiating, sharing. Cooperation was no longer a convenience, it was evolution's new frontier. Those who could connect, empathise and collaborate survived better than those who could not. The archaeological record of this time shows increasing uniformity in tool design across distant regions. Acheulean hand axes gave way to more regionalised flake industries, but the underlying techniques reveal shared logic. It's as if innovation had become collective. Someone, somewhere, discovered a new way to prepare a core, and soon, hundreds of kilometres away, others were doing the same. The network moved ideas as easily as objects. To imagine this world is to picture a continent alive with motion. Small groups, rarely more than a few dozen individuals, travelling seasonally, crossing paths at water sources, sharing news without speech. Children might have learned gestures and rhythms that transcended dialects. Elders may have mediated exchanges with ritual gestures, perhaps even with song. The foundation of humanity's future, cooperation through communication, was already being built, one silent encounter at a time. And yet, this was still a fragile intelligence. Climate chaos could scatter these connections overnight. A drought might drive one group north, famine might erase another. But even when the people vanished, the pattern endured. Each time populations met again, they carried memory, not in stories, but in habits. The shape of a tool, the preference for a certain pigment, the way a gift was offered. Culture outlived individuals. The more archaeologists study these sites, the more they realise that the great leap toward modernity did not happen suddenly around 50,000 years ago as once believed. It was already happening here, 200,000 years earlier, in quiet, cumulative steps. Symbolism, cooperation, and shared identity were not products of civilization. They were the conditions that made civilization possible. It is humbling to think that so much of what defines us began in silence. Before there were words, there were gestures, glances, and gifts. Before there was art, there was colour. Before there was trade, there was trust. The humans of this age, our distant kin, had already learned that survival meant belonging. The landscape may have been harsh, but their minds had found warmth in connection. If you could stand among them, watching the sun fall behind the hills of the Rift Valley, you might see small groups converging from different directions. They greet not with speech, but with the exchange of an object, a stone, a pigment, a bead. Around the fire, the night hums with the same quiet cooperation that still binds us now. They may not have had language, but they had meaning, and that was enough to make them human. How does a species invent community before it invents words? Perhaps by realising that meaning doesn't start with sound. It starts with understanding. The red pigment, the obsidian shard, the shell bead, all were early sentences in the long unspoken story of us. Imagine this, an entire continent breathing in and out, its rivers shifting, its forests thinning, its deserts crawling slowly across the horizon like tides of dust. From above, Africa during this time would have looked alive, expanding and contracting in rhythm with the planet's pulse. lakes that once stretched for hundreds of kilometres dried into salt pans, then returned as freshwater seas. Forest belts retreated to mountain slopes, while savannas opened into endless golden plains. And through all this, small human groups, our own ancestors, scattered, split, and survived, isolated from one another for thousands of generations. Yet somehow, they never lost the memory of being one species. Between 200,000 and 100,000 years ago, Earth entered a period of deep climatic oscillation. The planet's orbit around the Sun wobbled, its tilt shifted, and the great rhythms of glacial and interglacial cycles intensified. Scientists call this interval marine isotope stage 5, or MIS5, a time of extreme contrasts when the African climate swung between humid abundance and devastating drought. Every few tens of thousands of years, monsoons would surge northward, filling once dry basins with water and greening the Sahara. Then, just as quickly, the rains would vanish, leaving behind parched wastelands and fragmented ecosystems. These changing conditions shaped not only the landscape but the pattern of human life upon it. During wetter periods, lush corridors connected the continent from coast to coast, allowing populations to move, meet, and mix. During dry intervals, deserts and arid plains cut them off, isolating groups for millennia at a time. It was a cycle of connection and separation, a continental heartbeat that forged diversity from distance. Genetic studies suggest that early Homo sapiens were divided into several regional populations during this time, not by hostility, but by geography. Each group adapted to its own environment. In the south, near what is now the Kalahari and Cape regions, human communities thrived along coastal refuges rich in shellfish and plants. In the east, populations followed the Rift Valley's lakes and rivers, living among volcanic highlands that offered shelter and obsidian for tools. In the north, near the Sahara's fluctuating edge, others endured alternating wet and dry periods, retreating into mountain oases when the desert returned. These isolated groups followed different paths of evolution. Subtle anatomical differences appeared, variations in skull shape, limb proportions and facial features, none distinct enough to form separate species, but enough to show that evolution was experimenting. Diversity was not a side effect of isolation. It was the engine of adaptability. Every refuge and every small pocket of survival became a workshop where natural selection tested solutions for endurance, cognition, and cooperation. When climate eased and green corridors reopened, these groups met again. They exchanged mates, genes, and knowledge, blending their unique adaptations into the broader genetic fabric of humanity. This pattern of divergence and reconnection, isolation and reunion, created a species both unified and diverse. It is one reason modern humans carry such deep genetic variation, especially within Africa itself. The DNA of people living today still bears echoes of those ancient intervals of separation. Archaeology supports this genetic mosaic. In eastern Africa, sites such as Ologisaili in Kenya and Gadamota in Ethiopia show evidence of technological transitions around this time, from large Acheulean hand axes to more refined Middle Stone Age tools, including points, blades, and pigment use. In southern Africa, the coastal refuges of Pinnacle Point and Clayses River preserve traces of early modern humans exploiting shellfish and using heat-treated stone to create sharper tools, some of the earliest examples of complex resource planning. Meanwhile, in Central and Western Africa, few sites survive, but the sparse finds suggest continued adaptation to rainforest and savanna environments. The remarkable part is how these innovations often appear independently, then spread after climatic connections return. When humid faces reopened travel routes, the exchange of ideas likely accelerated. Pigments from the south appear in eastern contexts. tool types first seen in the rift reappear in the far west. This circulation of culture across ecological frontiers shows that our ancestors were not static bands of survivors but active participants in a continental network, one that stretched from the Mediterranean to the Cape long before written maps existed. Paleo-environmental data from lake cores and cave sediments confirm how dramatic these cycles were. At Lake Malawi, for example, sediments reveal alternating layers of diatom-rich muds from wet periods and coarse sands from dry ones. These records match the genetic evidence for fluctuating population sizes. During hyper-arid phases, human numbers crashed, a genetic bottleneck. But each recovery brought new recombination. Survival depended on flexibility, on remembering how to adapt when the world changed again. It is here, during this time of oscillation, that we begin to see the full power of behavioural versatility. The humans who lived through 𝐓𝐈𝐌𝐿 had to understand pattern, not just in nature but in time. They learned that droughts returned, that rivers dried and filled again, that herds migrated in rhythms larger than a lifetime. To endure meant to anticipate. The brain evolved not just to react, but to remember across generations. In a sense, Africa itself became the teacher. Its shifting climate forced humans to evolve not around stability, but around instability. Intelligence, cooperation, and creativity were no longer luxuries. They were survival tools. Each isolated group learned to live within its specific microcosm, developing unique knowledge systems about plants, animals, and seasons. When they reconnected, these local insights merged, creating cultural synergy. Isolation had not weakened humanity. It had diversified its imagination. The evidence for this lies in the stone record's growing complexity. Across Africa, toolkits became more regional, more specialised, and more adaptive. Some groups experimented with hafting, attaching stone tips to wooden shafts for greater leverage. Others refined heat treatment, using fire to improve the flaking properties of stone. These innovations likely spread during contact phases, their diffusion visible in archaeological timelines that leap across thousands of kilometres. Behind each technique lies an unspoken language of shared observation, the beginning of teaching as we know it. Even the pigments of this era carry the story of diversity through isolation. Different regions favoured different sources of ochre: hematite in the south, limonite in the east, guthite in the north. Each required unique methods of grinding, heating, and application. The variety suggests not uniform ritual but localised traditions, each expressing identity within a broader species unity. In this way, technology and culture became markers of ancestry long before writing or genealogy existed. Genetically, this period also marks the deep branching of human lineages still detectable today. Modern African populations, such as the San, Hadza, and Mbuti, preserve some of the oldest mitochondrial and Y chromosome lineages, tracing back to these early subdivisions. Their diversity is not recent. It is ancient, born of those 100,000-year intervals when the continent splintered into ecological islands. And yet, across all these differences, the capacity for empathy and cooperation endured. When groups met again, they recognised one another not as strangers, but as distant kin. What makes this chapter in our story so profound is how it reframes the meaning of unity. Humanity did not survive because it remained the same. It survived because it learned how to become many things at once. The environment divided us, but it also trained us to reconnect. Out of separation came resilience. Out of difference came creativity. By the end of this period, around 100,000 years ago, Homo sapiens was no longer an emerging form. It was established genetically and anatomically modern. Yet its strength lay not in uniformity, but in diversity. Africa had become a living archive of adaptation, a continent that encoded within its people every lesson it had ever taught. Endurance in drought, curiosity in abundance, and cooperation in reunion. If you could walk through that world, across the wetlands of the Rift, through the dunes of a shrinking Sahara, along the rocky coastlines of the south, you would find scattered human camps, each slightly different, yet all recognisably ours. One group boiling shellfish, another shaping obsidian, another marking stones with red pigment. They would not have spoken the same words, but their gestures would have been familiar. Laughter, generosity, the shared act of looking at the same stars. What happens when a species fragments but never forgets itself? It becomes something stronger than geography, a pattern of survival written across space and time. Those intervals of isolation were not interruptions in our story. They were the story, the rhythm that made a continent of many people into one humanity. The wind has carried salt for the first time. The air tastes different. Ahead, beyond dunes and heat, there is a horizon that gleams, not of sand, but of water. To reach it, humans had already crossed mountains, grasslands, and desert plateaus. But this was different. This was the edge of everything they knew, a shimmering boundary between land and the unknown. For the first time, one of our ancestors stood at the Red Sea and realized the world continued beyond the horizon. Between 100,000 and 70,000 years ago, the African continent changed once again. Not through catastrophe, but through opportunity. The world's orbit, its tilt, and its distant glacial rhythms conspired to create corridors of green stretching from East Africa into Arabia. Rain returned to the deserts, rivers carved paths across the Sinai and the Horn of Africa. Lakes that had been dust for millennia filled with water once more. It was not a migration yet, more a slow drift, a following of shorelines and freshwater. But for the first time in nearly 2 million years, a hominin species, our species, stood ready to leave Africa behind. In this window of time, the climate gave humanity a chance, and technology made that chance possible. The archaeological record shows a quiet revolution along the eastern coast of Africa. Sites like Pinnacle Point and Mumbo Cave reveal evidence of people exploiting marine life, shellfish, fish, and seabirds. To do this, they had to understand tides, collect tools for digging and prying, and navigate the dangers of coastal cliffs and waves. They had to think in patterns beyond the immediate. To gather mussels or hunt fish meant waiting for low tide, knowing when to return. The coast was both a resource and a teacher, and in its rhythm humans learned patience and planning. The evidence from Pinnacle Point shows that people there used fire to heat-treat stone, a technique that made it easier to flake predictably. This innovation, first appearing around 160,000 years ago and refined into this later period, allowed for smaller, sharper, lighter tools, blades and microliths suited for mobility. Combined with hafting, this technology meant that groups could carry efficiency in their hands. They could adapt faster, move farther, and exploit new landscapes more effectively. It is easy to imagine how such tools changed their world. A sharpened point made from heat-treated silkreed could pierce hide, open shellfish, and cut sinew, all with minimal effort. But more importantly, the process of making it required high-temperature control and forward planning. One does not accidentally invent heat treatment. It must be taught, observed, and remembered. Each generation carried knowledge not in bones but in rituals of creation, fire, stone, patience. The coastal adaptation seen in Africa spread northward, along what would later become the Bab el-Mandeb Strait, the narrow sea passage between modern Djibouti and Yemen. During glacial lows, sea levels dropped dramatically, shrinking this channel to as little as a few kilometres across. Geological reconstruction suggests that at times one could see the opposite shore shimmering through the haze. The distance was short, but the idea, crossing water, was immense. At sites such as Jebel Faya in the Arabian Peninsula, archaeologists have discovered stone tools dated to around 120 to 80,000 years ago. Their design mirrors African Middle Stone Age industries, suggesting not coincidence, but continuity. Similar finds at Al-Wustra and Dhofar reinforce this connection. Humanity had begun to spill beyond the continent, following rivers and coastlines into Arabia. The movement was not a single exodus, but a pulse. Groups advancing during wet intervals, then retreating when aridity returned. Arabia, with its lakes and monsoon-fed valleys, was a temporary extension of Africa itself. Green for a while, then lost again to desert. The humans who made this journey were not explorers in the modern sense. They were foragers following opportunity, moving gradually through familiar habitats, not yet realizing they were crossing into a new world. The Red Sea did not divide them as it divides continents today. It was a permeable boundary, shifting with sea levels and wind. Shell middens and obsidian tools along both coasts suggest repeated crossings, perhaps using simple rafts or by walking over exposed shallows. To them, the passage would not have felt like discovery, just another step along a river, another horizon reached. What makes this moment so profound is that it was not inevitable. For hundreds of thousands of years, humanity had been content or constrained within Africa. Climate barriers, deserts, and population limits had prevented sustained expansion. Yet here, in this narrow window, everything aligned: brain, tool, and climate. The people standing at those shores were anatomically modern, technologically competent and cognitively flexible. They had language in some form, if not fully modern syntax, then rich communication systems capable of planning, coordination, and teaching. They could survive in varied environments and adapt their diets. The world, once a mosaic of local ecosystems, had become navigable. Still, the crossing was not a mass migration. The population of all Homo sapiens alive at the time may have numbered fewer than 100,000 individuals, scattered in small, semi-isolated groups. Only a few likely made the journey east, leaving faint archaeological traces. Yet from these few would later arise the global dispersal that reshaped the planet. Arabia and the Levant became the testing ground, the first proving ground of what it meant to be human in new lands. In the Levant, at sites such as Skul and 𝐓𝐾𝐒 in modern Israel, human fossils dated to around 100,000 years ago reveal faces unmistakably ours. Delicate chins, rounded skulls, modern proportions. These individuals lived in a landscape of oak forests and river valleys, hunting gazelle and deer, burying their dead with care. They represent an early wave of humans expanding into Eurasia long before the Great Migration that would occur tens of thousands of years later. Their presence was brief. Climate shifts and competition would drive them back south, but their memory remains in stone and bone. Archaeologists describe these early dispersals as failed in demographic terms, but that word feels misplaced. Failure suggests an ending. Yet every attempt, every movement, left genetic and cultural footprints that shaped what came next. The genes that survived in Africa were mixed, tested, and strengthened by the very adaptability these journeys required. Each return carried knowledge, new tools, new strategies, new awareness of the world scale. Humanity was learning that the Earth was not a cage, but a web. By 70,000 years ago, the wet corridors closed again. Deserts expanded, rivers dried, and the green pathways through Arabia faded back into sand. Populations in the north retreated, perhaps returning south into Africa or clustering near coastal refuges where moisture lingered. But something had changed permanently. Humans had reached the world's edges and found they could endure even there. Genetic evidence hints that some of these early populations may have left faint traces in modern humans. Small fragments of DNA preserved like whispers of earlier journeys. Whether those specific lineages survived or not, the cognitive readiness did. The mind that crossed the Red Sea would soon cross everything else. The image of those first humans standing on a rocky shore watching the tide shift is almost too symbolic, yet it is likely true. At some point, someone somewhere took that step, maybe walking through shallow water, maybe clinging to driftwood, maybe chasing birds that led them to another shore. That moment, quiet, unrecorded, ordinary, was the first expansion of consciousness beyond a single continent. It was not conquest or escape, it was curiosity. How does an inland wanderer find the edge of the world? By following the logic of life itself, to move, to adapt, to see what lies beyond the next horizon. The humans of that age could not have known they were beginning a story that would span the globe. They were simply continuing what their ancestors had always done, moving toward water, warmth, and survival. The difference now was that they carried the memory of connection, the skills to endure isolation, and the imagination to cross boundaries that were no longer only physical. And when they looked east into the vast glow of dawn over the sea, they were looking, for the first time, at the rest of human history waiting to unfold. The roots of humanity spreading like a web across continents, not as a single trail from one birthplace, but as a slow, tangled branching of bodies, bones, and minds. What if Africa was not the only cradle, but simply the one that remained? What if, scattered across ancient Europe and Asia, there were other experiments in becoming human, cousins so close that their echoes still linger in our DNA, in our bones, in our doubt? The story of our origin, though centred in Africa, has always been chased by counter-theories, some grounded in data, others in hope. And like any good mystery, they force us to ask whether the map of evolution is more mosaic than migration. The first whisper of an alternate story begins deep in time, around 11 million years ago, in the ancient forests of what is now Germany. There, in the clay beds of Hammerschmiede, paleontologists unearthed a creature unlike any other known ape, Danuvius guggenmosi, a primate with long, flexible limbs and a pelvis shaped for partial bipedalism, lived in the late Miocene, long before the first hominins of Africa. Its fossils suggest it could both hang from branches and walk upright along them, a strange hybrid of climber and walker. Some scientists have proposed that this species, or others like it in Europe, may represent an early form of locomotion that later gave rise to the line leading to humans. The European origin hypothesis suggests that upright walking may have evolved in the wooded environments of southern Europe before spreading into Africa through ancestral migrations. Other fossils, such as Uranopithecus from Greece and Gracopithecus from the Balkans, have added fuel to the idea. These apes lived between 9 and 7 million years ago, and some features of their jaws and teeth, thick enamel, short faces, vaguely resemble early hominins. A 2017 study of Gracopithecus even claimed that its dental roots were fused in a pattern more similar to humans than to other apes, leading to headlines suggesting that the first human might have been European. But science moves cautiously. For every bold hypothesis there are counterweights. The evidence for these European species remains fragmentary. A few teeth, a partial jaw, a femur fragment. The fossil record is sparse, and dating methods uncertain. It is equally possible that these apes were simply regional offshoots, evolutionary dead ends rather than ancestors. Still, their existence reminds us that the late Miocene was not a world divided by species or continent, but a continuous belt of forest stretching from Spain to East Africa, home to a vast radiation of apes, many of which are now lost. The second great counter-theory emerges from the east. Asia, too, holds fossils that challenge the simplicity of the out-of-Africa narrative. Homo erectus, first discovered in Java by Eugène Dubois in the late 19th century, remains one of the most enduring mysteries in human evolution. These ancient humans appeared in the fossil record as early as 1,800,000 years ago, long before modern humans existed. They lived from Indonesia to China for over 1 million years, an extraordinary tenure. The multi-regional hypothesis, proposed in the mid-20th century, suggested that Homo erectus populations in Asia evolved gradually into Homo sapiens through continuous gene flow with other regions. In this model, humanity did not have a single birthplace, but multiple, interconnected centres of evolution. This view gained traction in an age before genetics could arbitrate such claims, when fossils were the only record we had. The discovery of the Zhoukoudian and Peking man fossils in China seemed to support it, a lineage of upright, intelligent toolmakers living through long spans of time, perhaps slowly becoming more human. Even today, new discoveries from Asia blur the edges of this idea. At Dmanisi in Georgia, fossils of Homo erectus dated to around 1,800,000 years ago reveal a surprising diversity of skull shapes, suggesting flexibility within the species that might have allowed for adaptation and continuity across vast regions. In Indonesia, on the island of Java, late surviving Homo erectus fossils dated to less than 100,000 years ago show that these populations persisted long after modern humans had already appeared in Africa. Could isolated groups of Homo erectus have independently developed human-like traits? It remains debated, but the persistence of this species across continents hints at evolutionary parallelism, similar outcomes arising under similar pressures rather than direct descent. Then there are the fossils that complicate things even further. Modern-looking bones found outside Africa long before the Great Dispersal that began 70,000 years ago. The site of Apidema in Greece revealed a skull fragment that, according to modern dating techniques, may be around 210,000 years old, older than many African Homo sapiens fossils. Its rounded cranium and lack of heavy brow ridges make it distinctly human-like. Likewise, fossils from Israel's Mislia cave, dated to around 180,000 years ago, also appear to belong to early Homo sapiens. These finds suggest that humans, or at least human-like populations, ventured into Eurasia far earlier than previously believed, in waves that rose and receded with climate. Some researchers interpret these fossils as evidence that our species emerged not from a single African origin, but from a web of populations spread across Africa, the Near East, and perhaps beyond. They envision evolution as a braided stream, lineages diverging and reconnecting, exchanging genes across continents whenever climate allowed. In this view, Africa remains central, but not exclusive. It is the core of a much larger ecological and genetic network. And yet, despite these provocations, the balance of evidence continues to point back to Africa. Ancient DNA, whenever available, tells a consistent story. The deepest genetic lineages, those with the most time to diversify, all trace to African populations older than 200,000 years. Fossil morphology, too, follows the same gradient. The earliest clearly modern humans appear in Africa, while fossils outside it show mixtures or later arrivals. The European and Asian finds, while tantalizing, may represent early excursions, migrations that fizzled or hybridized but did not replace the African root. Even Danuvius, the so-called European proto-human, fits comfortably into this picture when seen through the lens of ecology rather than rivalry. Bipedalism may well have evolved in multiple forms among Miocene apes, as an experiment in efficiency, but the lineage that led to humans took hold in Africa, where shifting savannas and variable climates made upright, walking a long-term advantage. Likewise, Asian Homo erectus was extraordinary, but its isolation on islands like Java turned it into a separate, enduring branch rather than a precursor. Science, in its best form, thrives on such tension, on hypotheses that stretch against consensus. Every counter-theory, whether ultimately right or wrong, forces the story to become sharper. The debates around Europe, Asia and Africa are less about competition than about scale. How many times did nature attempt to make something like us? and how many of those attempts nearly succeeded. In this way, the history of our origins is not a single ladder but a forest, a living tangle of evolution, where some branches reach sunlight while others wither. Africa provided the deepest roots, the continuity of climate and time. Europe and Asia hosted experiments, brief and brilliant. Each tells part of the truth. Together they remind us that becoming human was not an event but a process, one that spanned continents and millions of years of trial. If one were to draw a map of our ancestry, it would not be a single arrow leaving Africa, nor a circle of confinement, but a pulse, out and back, branching and merging, a global rhythm of adaptation. The fossils of Danuvius in Europe, the tools of Homo erectus in Java, the bones of early humans in Greece and Israel, all are notes in the same unfinished melody. Could the story have started somewhere else entirely? Perhaps in fragments it did. Perhaps the urge to walk upright, to shape stone, to think ahead, was written into the primate genome long before any continent claimed ownership of it. But when we look at the continuity of data, the genetics, the climate archives, the fossils, one truth remains clearest. Africa was not the only cradle, but it was the one that kept the fire alive. Imagine this. Every heartbeat you've ever felt, every cell dividing quietly in your body, still carries a small memory of Africa, not as a place on a map, but as a pulse. The soil may have changed, the continents drifted, but inside you remain a geography that never left. It's strange to think that the most recent parts of us, our thoughts, our technologies, our illusions of separation, were built upon the oldest foundation nature ever laid for us. If there is one truth that holds through all the bones, the stones and the dust, it's that Africa is not behind us. It's within us, a continent made of time, not land. For billions of years before the first ape stood upright, the planet was already preparing the ground for what would become us. Africa's crust is among the oldest on Earth, its rocks holding memories of oceans that vanished before any eye could see. The rift valleys that later cradled early humans were once deep scars of tectonic movement, stretching slowly as if the planet itself were exhaling. Each fracture, each volcanic eruption, each monsoon cycle became part of the long experiment that sculpted intelligence. What began as geology became biology, and what became biology became memory. Our blood chemistry still carries the traces of this terrain. Iron, magnesium, sodium, the same minerals that stained ancient rivers red or built the basalt of the Rift Valley, flow through our veins in miniature oceans. The very balance of salts that keeps neurons firing today is a quiet echo of the inland seas where the first primates climbed. Even the hemoglobin that binds oxygen was once a byproduct of early microbial life that evolved under African heat. We don't just come from that environment, we still operate by its chemistry. Genetics, too, whispers the same story. Every human genome on Earth is a palimpsest, written first in Africa. The oldest mitochondrial lineages, those maternal sequences that connect us through an unbroken chain of mothers, trace back to small populations living somewhere in East Africa more than 150,000 years ago. Their names in science sound cold. L0, L1, L2, but what they represent is astonishing. Every person alive is part of a single, continuous biological thread that began there. When populations left the continent, they carried only fragments of that genetic variation, like small shards of a larger mosaic. Even now, Africans hold the deepest diversity of all, a genetic time capsule of nearly the entire species. If you could travel backward through your DNA, strand by strand, you would eventually reach a fork in the ancestral road where all paths merge, not in a single tribe or woman, but in a tangled web of ancestors who all called Africa home. The genetic clock that measures these divergences is not a human invention. It's the rhythm of mutation itself, ticking quietly through every replication, every generation. The code within us does not lie, but it does hum, and its melody is African. Yet the story of Africa inside us is not just about origins, it's about endurance. Our physiology still bears the fingerprint of the climates that shaped us. The way we sweat, the way our pupils constrict, the density of our bones, all tuned by the ancient dance of heat and drought, sunlight and shadow. Even our emotions may carry ancestral imprints. Stress, curiosity, cooperation, all survival mechanisms honed by a land that demanded flexibility over perfection. Africa never offered comfort, but it offered time, and time created adaptation. If we step back and listen, the fossil record becomes a kind of heartbeat itself, a pattern of disappearance and persistence. Species came and went, but something in the pattern endured, the habit of learning from change rather than fighting it. That may be the most African trait of all, the ability to survive not through dominance but through adjustment. In that sense, we still live by the laws of the rift. We move, we adapt, we share, we migrate, and in every motion the old landscape lives on. Archaeology reminds us that Africa was never a single beginning, but a vast conversation between scattered populations. Thousands of groups once lived across deserts, forests and coasts, separated by distance yet connected through exchange. Obsidian passed from one valley to another. Shells crossed hundreds of kilometres inland. Pigments travelled with stories no one remembers. Long before language, information itself evolved, not as speech, but as continuity. This ancient network of sharing became the nervous system of our species. Even the internet, if you squint through enough geological time, feels like an echo of those early trade routes, the same hunger to connect, just at a different scale. And still, the deeper we dig, the more we learn how provisional all this is. Fossils redate, new ones appear, genes tell different tales with every sequence added. The truth of our origins is not a fixed monument, but a tide that keeps revealing new shores. Science doesn't settle. It expands like Africa itself once did when it split and drifted to form the continents. To study where we came from is to accept that certainty is temporary, that knowledge, like life, keeps evolving. So what does forgetting mean? Perhaps it's when we begin to see Africa as somewhere else, a distant chapter instead of the entire book. Forgetting is when we start to believe that we ever left. Every culture, every skin tone, every language is just another reflection of how the continent's legacy diversified itself. We did not outgrow Africa, we extended it. Our cities, our satellites. These are new ecosystems, built on the same restless intelligence that first emerged under African skies. If you could strip away the centuries of migration and myth, if you could hold a mirror up to the genome, you'd see not nations or races, but rivers of ancestry flowing in every direction, all beginning in one geological basin of time. Even as we split apart, we carried its pattern with us, the ability to adapt, to wonder, to build meaning from chaos. The African landscape was the first teacher of that lesson, not through words, but through weather. Every drought, every shift in monsoon, every volcanic ashfall forced the species to innovate, and it was in that cycle of scarcity and renewal that intelligence was tempered. To remember Africa, then, is not to romanticize the past, but to recognize the mechanics of our own survival. It is the ongoing experiment that built a brain capable of remembering itself. Perhaps that's why Africa feels less like a place in human history, and more like a presence. Every discovery, every fossil unearthed, every gene sequenced seems to whisper the same line. You were never separate. The continents changed, but the lineage did not. The neurons that spark your curiosity today are descendants of that same curiosity that once noticed a crack in a shell, pattern in the stars, or the warmth of a flame against the dark. Africa is the continuity of noticing. If one day we reach other worlds, step onto alien soil under another star, we will still be carrying it. The ancient reflex of adaptation, the deep memory of change. In that sense, the continent inside us is not made of soil or species, but of awareness. We're not just from Africa. We are its echo, its latest experiment in memory. And so, when you close your eyes tonight, think of the dust in your bloodstream, the minerals beneath your nails, the quiet architecture of your own cells. They are older than any story, older than any name. You do not simply descend from Africa. You're a fragment of its geology that learned to think, and as always, stay curious, stay calm. I'll see you in the next story.